When people think of planetary rings, their minds immediately leap to Saturn, the celestial crown jewel, the most spectacular natural structure in the solar system, visible even through small backyard telescopes. For centuries, Saturn's rings have captivated scientists, artists, and poets alike, dazzling in their breadth and brilliance. But Saturn is not alone. Every giant planet has rings. Jupiter, Uranus, and Neptune each carry faint encirclements, discovered only in the last few decades. These lesser-known systems are not luminous masterpieces like Saturn's, but shadowy sketches, delicate etchings almost invisible against the black canvas of space. By comparing them, we learn not only how rings differ, but also why they exist at all, and why they embody the theme of ephemeral beauty. Saturn's rings are unmatched in scale and visibility. They stretch over 280,000 kilometers from the planet's center, yet remain astonishingly thin, often no more than a few tens of meters thick. Composed mostly of water ice, with a sprinkling of dust and organic compounds, they reflect sunlight brilliantly, giving Saturn its iconic radiance. Observed since Galileo's crude telescope in 1610, they were at first a puzzle. Galileo sketched Saturn with ears or handles, not understanding what he saw. It was Christian Huygens in 1655 who correctly proposed that Saturn was surrounded by a thin, flat ring. Later, Giovanni Cassini identified the gap that bears his name, revealing structure and dynamism where others saw a uniform halo. By the time spacecraft like Voyager and Cassini arrived, Saturn's rings had become more than astronomical curiosities. They were natural laboratories, revealing spiral density waves, moonlet-induced propellers, and patterns sculpted by gravity's invisible hand. Yet if Saturn dazzles with brilliance, Jupiter startles with subtlety. Jupiter's rings were invisible to telescopes until Voyager 1 flew past in 1979. Instead of grand icy arcs, Jupiter's rings are composed of fine dust particles only microns across, constantly replenished by micrometeorite impacts on its small inner moons, Metis, Adrastea, Amalthea, and Thebe. These impacts throw debris into orbit, forming three main components: a thin main ring, a diffuse halo of dust spiraling inward, and gossamer rings associated with Thebe and Amalthea. From afar, they are ghost-like, faint arcs detectable only when sunlight scatters off their tiny grains. Unlike Saturn's icy brilliance, Jupiter's rings are dusky, delicate and transient, a quiet adornment more akin to smoke than jewelry. Their fragility speaks to continual renewal. Without constant resupply, they would vanish in a few thousand years. Uranus's rings are even stranger. Discovered not by spacecraft but in 1977, when astronomers observed a star's light blink as Uranus passed in front, they appeared as thin, dark arcs that puzzled scientists. Unlike Saturn's broad bands or Jupiter's diffuse dust, Uranus's rings are confined into narrow ribbons, some only a few kilometers wide. The brightest, the Epsilon ring, remains sharply bounded, as though sculpted by unseen hands. Voyager 2's 1986 flyby confirmed their existence, showing 11 main rings made of dark, carbon-rich material that reflects little sunlight. Unlike Saturn's icy mirror, Uranus's rings are charcoal shadows, invisible, except during rare occultations or with the sharpest instruments. They seem fragile, temporary, and carefully corralled, perhaps by shepherd moons like Cordelia and Ophelia, which keep them confined against the spreading effects of collisions and orbital drift. Neptune, the Storm King, carries rings that are fainter still, but with a twist. When Voyager 2 flew by in 1989, it confirmed 5 main rings, all dark and dusty like Uranus's. But Neptune's rings contained something that defied expectations: clumpy arcs. Physics predicts that ring material should spread evenly along its orbit, forming smooth bands. Instead, Neptune's Adam's ring contained arcs of brighter material, clustered segments that refused to disperse. How could this be? One explanation is that the moon Galatea, orbiting just inside the ring, acts as a shepherd, its gravity corralling particles into arcs. Another possibility is that collisions and resonances constantly refresh the clumps. Whatever the cause, Neptune's arcs remain one of the solar system's puzzles. Structures that by all rights should not exist, yet stubbornly persist. They remind us that even in something as simple as dust circling a planet, nature delights in breaking expectations. Comparing these four systems reveals striking contrasts. Saturn's rings are ancient masterpieces of ice, bright and broad, sculpted into thousands of features by moons and resonances. Jupiter's rings are ephemeral halos of dust, subtle and smoky, born of impacts on small moons. Uranus's are narrow shadows, confined arcs of darkness, sharp-edged and mysterious. Neptune's are broken necklaces, clumpy and uneven, their very existence a paradox. Together, they show that rings are not one phenomenon but many, shaped by composition, history, and environment. Why is Saturn so spectacular while the others are so muted? The answer likely lies in composition and age. Saturn's rings are 95 to 99% pure water ice, producing their extraordinary brightness. The other giant's rings contain darker, rocky or carbon-rich material, reflecting little light. Saturn's rings may also be younger, perhaps only 100 to 200 million years old, formed when a moon was torn apart by tidal forces or shattered by impact. Their youth would explain their brilliance. Time has not yet coated them with dust and radiation-darkened organics. Jupiter, Uranus, and Neptune may once have had brighter rings, but billions of years of cosmic weathering have dulled them, leaving faint remnants. If so, we live in a fortunate era, one when Saturn's crown shines at its peak. Culturally, Saturn's rings have become the icon of planetary beauty, inspiring art, literature, and awe. Galileo's puzzled sketches, Cassini's crisp photographs, and Cassini-Huygens's final dive have cemented them in human imagination as a symbol of cosmic elegance. The other rings, faint and ghost-like, remain largely unknown to the public. Yet in their subtlety lies their own poetry. Jupiter's dusty veils, Uranus's invisible bands, Neptune's impossible arcs, each an artwork of a different style. If Saturn's rings are the baroque grandeur of a cathedral, Jupiter's are whispers of smoke, Uranus's minimalist sketches, Neptune's impressionistic fragments. Together they form a gallery of cosmic art, each planet a canvas where gravity, time, and matter paint their designs. In science and philosophy alike, rings remind us that beauty is not uniform. It wears many faces: brilliance, shadow, clump, and arc. Saturn dazzles us because it is bright. The others intrigue us because they are hidden. To compare them is to realize that the solar system itself is an art gallery, filled with works in every style, some obvious, some subtle, some baffling. The lesson of rings is the lesson of diversity, that wonder takes many forms, and each deserves its place in the story of worlds. If rings are artworks, then moons are their sculptors. These small companions, orbiting near or within ring systems, exert a gravitational influence that shapes, confines, and animates the rings. Without moons, many ring systems would disperse into featureless bands of dust. With them, rings become intricate structures of gaps, edges, waves, and arcs. To watch rings is to watch a ballet of resonance, where every ripple and every boundary speaks of a nearby moon, tugging invisibly at particles of ice and dust. The concept of shepherd moons is central. Like dogs guiding a flock, these moons corral ring particles, preventing them from spreading. Gravity pulls particles inward or outward, balancing their motion to keep the rings sharply confined. The most dramatic examples are found at Saturn, whose rings are both broad and exquisitely structured. The narrow F ring, for instance, owes its bizarre beauty to the interplay between two shepherd moons, Prometheus and Pandora. Prometheus orbits just inside the F ring, periodically diving into its edges, dragging out streamers of particles and creating scalloped structures. Pandora, on the outside, tugs back, pulling material outward. The result is a ring of chaos, strands, braids, and clumps that constantly shift as the moons herd the material between them. The F ring is not stable in the static sense. It is stable in perpetual motion, sculpted anew with each orbit. Other gaps in Saturn's rings also bear the fingerprints of moons. The Encke gap, a wide division in the A ring, is maintained by the tiny moon Pan. Orbiting inside the gap, Pan sweeps the region clean, its gravity ejecting particles or drawing them into confined streams. Similarly, the Keeler gap is sculpted by Daphnis, a small moon only 8 kilometers across. Despite its size, Daphnis produces spectacular waves along the edges of the gap. As it passes, particles are pulled upward and downward, creating vertical ripples hundreds of meters high, mountains in miniature carved into the icy sea. Cassini's close-up images revealed these ripples in exquisite detail, reminders that even the smallest moons can leave towering signatures in rings. Uranus's rings, faint and narrow, also show shepherding. The most prominent, the Epsilon ring, is bounded by two small moons, Cordelia and Ophelia. These shepherds ensure the ring's edges remain crisp rather than diffusing into space. Without their guidance, the Epsilon ring would spread within thousands of years, erasing its sharp profile. Instead, it persists, held in check by a delicate gravitational dance. Voyager 2 confirmed these shepherd moons, showing that even Uranus's dark and hidden rings are not immune to the sculptor's hand. At Neptune, shepherding takes on a mysterious role. The planet's Adam's ring contains the famous arcs, clumps of ring material that stubbornly refuse to disperse. Physics dictates that particles in orbit should spread evenly, yet the arcs persist. One explanation is that the moon Galatea, orbiting just inside the ring, acts as a stabilizer. Its gravity may confine the arcs into clumps, preventing them from diffusing. The precise mechanism remains debated, but Galatea's presence offers the best clue. Without it, the arcs would likely vanish. This makes Neptune's ring system a puzzle, where moons hold secrets still unsolved. Even Jupiter, with its faint dust rings, owes their existence to moons. The main ring is supplied by debris from Metis and Adrastea, two tiny moons orbiting close to the planet. The Gossamer rings are linked to Thebe and Amalthea. Without these moons, Jupiter would have no rings at all. Here, the shepherding role is not confinement, but replenishment. The moons continually feed the rings with dust struck loose by micrometeorite impacts. In this case, the moons are less sculptors than donors, giving of themselves to sustain Jupiter's ghost-like halos. What emerges from these examples is a portrait of collaboration. Moons and rings are not separate entities but interdependent. Rings shape moons as much as moons shape rings. Pan and Atlas, embedded within Saturn's rings, accrete icy material along their equators, giving them distinctive flying saucer shapes. Daphnis grows with the particles it disturbs, a child of the ring it sculpts. Even shepherd moons that orbit outside the rings are shaped by their duty, their orbit slightly perturbed by the very material they confine. In this sense, moons and rings are co-creators of beauty, locked in cycles of influence. The concept of shepherding also resonates beyond rings. Astronomers see similar processes in protoplanetary disks around young stars, where planets carve gaps and shepherd dust into rings. The same physics that lets Prometheus sculpt the F-ring also lets Jupiter-sized exoplanets carve pathways in dusty disks, visible in ALMA telescope images. Thus, shepherd moons are not only local artists, but cosmic prototypes, showing us how worlds form elsewhere. Rings become laboratories, moons their chisels, and together they etch the rules of planetary genesis. Philosophically, the shepherding role reminds us of the unseen hand. To the naked eye, Saturn's rings seem static, serene. But behind their elegance lies invisible work. Moons tugging, pulling, guiding, keeping chaos in check. It is a metaphor for order hidden in apparent stillness, structure born of perpetual struggle. The rings are not passive ornaments, but active canvases, their shapes maintained by a chorus of unseen companions. Culturally, the image of shepherd moons guiding rings carries poetic weight. In myth and literature, shepherds tend flocks, guardians of fragile beauty. Here, moons fulfill that role literally, tending flocks of ice and dust, ensuring they do not scatter into darkness. Saturn's Prometheus and Pandora even carry the names of figures from mythology. One the firebringer, the other the releaser of hidden sorrows, apt symbols for moons that disturb and guide. Neptune's Galatea, a sea nymph in Greek myth, likewise shepherds arcs in a sea of dust. Human imagination cannot help but see in these roles echoes of stories older than science. In the end, ring-moon interactions show us that art requires artists. Saturn's rings would not shine as they do without their moon's sculpting hands. Uranus's arcs would disperse, Neptune's arcs would vanish. Jupiter's rings would fade. The interplay of gravity, subtle yet persistent, is the brushstroke on the cosmic canvas. Without moons, rings are dust. With moons, they are artworks, dynamic and alive. Planetary rings are more than adornments. They are laboratories, scaled-down versions of the great processes of the cosmos, where we can observe in real time how matter clumps, disperses, collides, and resonates. To study Saturn's rings, or the faint arcs of Neptune, is to study the very principles that govern the birth of planets and stars. In rings, we see not only beauty, but physics laid bare. A gallery of natural experiments playing out on scales we can measure and understand. At the most basic level, rings reveal the tension between accretion and breakup. On one side is gravity, which pulls particles together, encouraging clumping into larger bodies. On the other is the planet's tidal force, which tears clumps apart inside the Roche limit. Within this critical distance, a moon cannot form because the planet's gravity exceeds the mutual pull of particles. Saturn's main rings lie squarely inside this limit. Every icy shard tries to join with its neighbors, to become something larger, but Saturn's pull rips them back into fragments. The result is a system in perpetual tension, frozen between creation and destruction. This tension gives rings their fragile beauty. Look closely, and you see patterns of waves, gaps, and edges, all products of particles constantly colliding and redistributing energy. Cassini revealed spiral density waves sweeping through Saturn's rings, like grooves on a vinyl record, created by resonances with distant moons. As a moon tugs rhythmically on particles at certain locations, it sets up waves that propagate through the ring material. These waves are miniature versions of the spiral arms seen in galaxies. The same physics, scaled down billions of times. Rings thus become analogues of galaxies, laboratories where gravity writes in ripples what it writes in stars. Rings also show us the microphysics of collisions. Each particle, ranging from dust grains to boulders, collides with others at gentle velocities. These countless impacts grind down larger pieces, redistribute angular momentum, and establish a balance of sizes. The interplay of collisions and gravity produces phenomena like propellers, disturbances caused by moonlets too small to clear gaps, but large enough to stir their surroundings. Cassini's images of these propellers, named after aviators like Santos Dumont and Earhart, showed gaps and wakes carved by unseen bodies only a few hundred meters wide. Here, within the A-ring, is a glimpse of moon formation in action, frozen at the edge of possibility. Such dynamics offer insight into protoplanetary disks, where planets form around young stars. In those disks, dust grains collide, clump, and grow, while resonances with young planets carve gaps and waves. The physics of Saturn's rings is the physics of planetary systems, made observable on human timescales. Watching how particles interact in Saturn's rings helps astronomers model how Earth itself once accreted, how Jupiter shaped the asteroid belt, and how exoplanets shape the disks we see around distant suns. Breakup, too, is a lesson of rings. Moons that stray too close are shredded into debris, joining the rings. Some scientists think Saturn's rings may have formed when a moon was torn apart, either by tidal stress or a collision with a comet. The same process may have created Uranus's and Neptune's rings. In this way, rings are memorials of destruction, beautiful remains of worlds that could not survive their proximity to giants. Yet destruction in rings is not final. The debris becomes art, rearranged into bands of ice and dust that outshine the original moon in splendor. Resonance is another theme rings illustrate exquisitely. Moons orbiting far outside the rings can sculpt them through orbital resonances. A particle in Saturn's rings that completes exactly half an orbit, for every orbit of Mimas. For example, feels regular tugs that accumulate, clearing the Cassini division. These resonances create edges, gaps, and waves that mark the rings like signatures. Again, the lesson extends outward. Resonances between Jupiter and asteroids shape the Kirkwood gaps in the asteroid belt. Resonances in exoplanet systems reveal hidden planets. In rings, resonance is not abstract. It is visible, a sculptor's tool etching patterns into ice. Even Saturn's ring rain is physics in action. Cassini showed that particles, pulled inward by electromagnetic forces, spiral into the planet, falling like snow. This rain changes Saturn's ionosphere, linking rings to atmosphere in a cycle of exchange. The process demonstrates how rings evolve and fade, reminding us that they are temporary. In the laboratory of Saturn, we learn not only about formation, but also about impermanence. Philosophically, rings as laboratories suggest that the universe gives us microcosms. To understand the vast, we study the small. Rings let us see processes we cannot watch in protoplanetary disks or galaxies, because those unfold over millions of years and billions of kilometers. But in rings, those same processes, accretion, breakup, resonance, occur visibly, measurably, within decades. The cosmos teaches by analogy, offering us a miniature classroom in our own backyard. Culturally, there is poetry in the idea that Saturn's rings are not just ornaments but lessons. The grooves of spiral density waves are like etchings of music, the rhythms of the cosmos written in ice. Propellers mark the attempts of moons to be, never quite able to escape Saturn's pull. Gaps show the power of resonance, absence speaking as loudly as presence. Saturn's rings, then, are not static jewelry, but dynamic chalkboards covered in the writing of gravity and time. In the end, rings remind us that physics is beautiful. Accretion and breakup, resonance and collision, these are not dry equations but living phenomena, painted across worlds. To study rings is to see the universe at play, sculpting and reshaping, creating and destroying. Saturn may be the most spectacular canvas, but Jupiter's faint dust, Uranus's dark arcs, and Neptune's clumpy segments are all laboratories too, showing us variations of the same experiments. Each ring system is a classroom, each particle a teacher, each gap a story of forces unseen. Among the most endearing characters in the story of planetary rings are the tiny moons that dwell within them. Unlike the large, stately satellites like Titan or Ganymede, these are small, irregular bodies. Pan, Atlas, Daphnis, Epimetheus, Janus, oddballs with shapes and behaviors as strange as their environments. They are sometimes called ring weirdos, moons born of rings, sustained by rings, and sculptors of rings all at once. They are the brush strokes and the brushes, co-creators of Saturn's artwork. Perhaps the most famous of these is Pan, the innermost of Saturn's major moons, orbiting within the Encke gap of the A ring. Only about 28 kilometers across, Pan is small, but Cassini revealed it as one of the most extraordinary-looking worlds ever seen. It resembles a flying saucer, a central core surrounded by a broad equatorial ridge built from ring particles that have accreted onto its surface. Over time, icy grains drifting through the gap settled on Pan's equator, building the ridge into a shape that looks artificial. This saucer shape is a direct product of Pan's intimate relationship with the rings. It is both a moon and a collector of ring debris. Pan's gravitational role is equally important. It sweeps the Encke gap clean, its mass clearing away particles within a narrow zone. Yet its influence extends outward. Pan's gravity perturbs the edges of the gap, creating waves and wakes that ripple hundreds of kilometers away. Cassini images show delicate scallops and ripples along the edges, drawn outward and inward as Pan passes. Every orbit, the little saucer moon sculpts anew, leaving the Encke gap not empty, but alive with structure. Next comes Atlas, orbiting just outside Saturn's main rings. Like Pan, Atlas has a strange flying saucer appearance, its equatorial ridge even more pronounced. Atlas collects icy material along its equator, but because it orbits just at the ring's edge, it also acts as a shepherd moon, influencing the sharp boundary of the A ring. Atlas's odd shape gives it a whimsical quality, as though Saturn's rings had produced toys as well as structures. Both Pan and Atlas remind us that, in the delicate environment of rings, gravity, collisions, and accretion, produce shapes unlike anything in the broader solar system. Then there is Daphnis, another moonlet in the A ring, orbiting within the narrow Keeler gap. Daphnis is only 8 kilometers wide, yet it leaves spectacular signatures. As it moves through the gap, its gravity pulls particles upward and downward, creating vertical waves along the gap's edges. These ripples rise hundreds of meters above the ring plane, mountains of ice within a sheet only tens of meters thick. Cassini's images of Daphnis revealed wakes, ripples, and disturbed streams of particles trailing behind it, like a ship's wake in water. Daphnis proves that even the tiniest moon can leave colossal marks, a reminder that size is not always proportional to influence. Saturn also hosts the peculiar pair Epimetheus and Janus, two moons that share nearly the same orbit just outside the main rings. Every few years they approach one another closely, but instead of colliding, they swap orbits, exchanging places in a delicate gravitational dance. Their co-orbital ballet is unique in the solar system, and their proximity to the rings influences resonances that ripple into Saturn's broad bands. Though not embedded within the rings like Pan or Daphnis, they show how moons and rings together form systems of intricate harmony, where no orbit is left untouched by others. These moons are not merely passive participants. They are likely products of the rings themselves. Pan and Atlas may have formed by accreting material from the ring plane, growing until they reached their current size. Daphnis and others may be remnants of larger bodies shredded by Saturn's gravity, survivors of tidal disruption, frozen just shy of destruction. In this sense, they are moons born from rings, sculpted by the same forces they now sculpt in turn. The concept of weird moons also applies in subtler ways to Uranus and Neptune. While we have not imaged tiny embedded moonlets there in the same detail, it is almost certain that such bodies exist, shepherding the narrow arcs of Uranus and stabilizing Neptune's impossible clumps. Galatea, for example, near Neptune's Adam's ring, is larger than Pan, but plays a similar role, confining arcs through resonance. Cordelia and Ophelia at Uranus confine the Epsilon ring. These are larger shepherds, but smaller Pan-like moonlets may well lurk unseen, too small for Voyager 2 to detect. One day, future spacecraft may reveal them, adding to the menagerie of ring weirdos orbiting the outer giants. For physics, these moons are more than curiosities. They represent the middle ground between ring particles and full-fledged moons. They show us how bodies grow within disks, how accretion stalls, and how gravitational interactions carve gaps. In protoplanetary disks, the same processes scale up. Planet embryos carve gaps, gather dust along their equators, and leave wakes behind. Pan and Daphnis are, in miniature, the same as Jupiter was billions of years ago when it first formed, carving its gap in the solar nebula. The weird moons of Saturn are fossils of planet formation in miniature. Culturally, these moons have charmed the imagination. Their shapes, ravioli, flying saucers, spaceships, seem whimsical, as though Saturn were toying with us. Cassini's images of Pan and Atlas were met with astonishment, memes, and affection. They seem less like cold natural objects than characters, odd companions in Saturn's grand ballet. They remind us that exploration is not only profound, but playful, that the cosmos produces surprises as delightful as they are strange. Philosophically, these moons suggest that edges are fertile. Pan lives in a gap, Atlas at the boundary, Daphnis between bands, and it is at the edges where creativity flourishes. They are neither ring nor moon, but both, products of thresholds. Their existence teaches that boundaries are not walls, but incubators of novelty, where forces meet to create something new. Just as life thrives at Earth's boundaries, coastlines, river mouths, ecotones, so too does cosmic creativity thrive at the edges of rings. In the end, the weirdos of Saturn's rings remind us that beauty comes in all scales. A moon only 8 kilometers wide can stir waves hundreds of meters tall. A flying saucer shape can arise naturally from slow accretion. A co-orbital dance can endure for billions of years. These moons are characters in the cosmic artwork of rings, brushstrokes that shape the masterpiece even as they emerge from it. They are proof that rings are not static bands, but living systems, where moons and dust co-create wonder. When we look at Saturn through a telescope, its rings seem eternal, icy hoops that must have circled the planet since time immemorial. Yet science tells a different story. Rings are not everlasting crowns, but ephemeral structures, transient artworks of the cosmos. They are born, evolve, and one day vanish. To see them is to live in a fortunate epoch, to glimpse a beauty that future skies may not hold. The impermanence of rings comes first from their youth. For decades, scientists debated whether Saturn's rings were primordial, dating back to the birth of the solar system, or much younger. Data from the Cassini mission has tilted the debate toward youth. Measurements of how much sunlight the rings reflect, how much dust has accumulated upon them, and how quickly they lose material suggest Saturn's rings may be no older than 100 to 200 million years. If true, they formed long after Saturn itself, perhaps during the age of dinosaurs on Earth. To human imagination, that is still vast. But in cosmic terms, Saturn's rings are newborn. How did they form? One leading theory is that a moon was destroyed, either torn apart by Saturn's gravity when it wandered too close, or shattered by a massive cometary impact. The debris spread into a disk of icy fragments. Over time, these fragments ground down into the brilliant ring system we see today. Another theory suggests the rings condensed from icy remnants of Saturn's formation, preserved inside the Roche limit. But Cassini's data, particularly its measurement of the ring's mass and the rate at which they are eroding, supports the idea of a relatively recent catastrophe. Saturn's glory may be the funeral veil of a lost moon. And just as they were born, the rings are also dying. Cassini's instruments detected a phenomenon called ring rain, streams of icy particles pulled from the rings into Saturn's atmosphere by electromagnetic forces. This invisible snow falls at a staggering rate, perhaps enough to empty the rings within 300 million years. Cassini's final orbits even flew through this rain, tasting the chemical signature of water, methane, and organics spiraling down. In real time, we witnessed a process of disappearance, rings becoming atmosphere, ice becoming cloud. Saturn's splendor is fading, drop by drop, into the planet it adorns. The other giants tell the same story, each in their own way. Jupiter's rings, faint halos of dust, are constantly replenished by micrometeorite impacts on its small moons. Without that resupply, the dust would spiral inward and vanish within mere thousands of years. Jupiter's rings endure not because they are stable, but because they are constantly remade. Uranus's rings, dark and narrow, are likewise fragile. Their sharp boundaries are preserved only by shepherd moons, and even those may not hold forever. Neptune's arcs are even more precarious, defying physics by clumping where they should disperse. Perhaps Galatea's shepherding maintains them. But if not, they may dissolve within centuries or millennia, disappearing before we return with spacecraft to see them again. This fragility makes rings deeply philosophical. They are spectacles, yet temporary ones, like fireworks frozen on a planetary scale. Saturn's rings may vanish within a few 100 million years, a blink in cosmic time. Uranus's arcs may already be in their twilight. Even Saturn's brilliance, so dazzling to us, is impermanent. Future civilizations, millions of years from now, may gaze at Saturn and see only a bare planet, the rings long gone. They may find it hard to believe such splendor ever existed, just as we marvel at stories of vanished worlds in myth. Our generation, our epoch, is privileged to see Saturn crowned. The impermanence of rings also teaches us about cycles. What is lost is not lost forever, but recycled. Particles fall into Saturn, feeding its atmosphere. Dust escapes Jupiter's rings, only to be replenished by new impacts. Collisions between moons spawn temporary arcs. The solar system constantly creates and erases rings, ephemeral halos around its giants. Rings are not fixed monuments, but phases, recurring chapters in planetary evolution. To see a planet with rings is to catch it in a moment of adornment, a transient costume in the long play of time. Culturally, this impermanence resonates. Humanity has always associated rings and halos with eternity, crowns of gods and kings. Yet in the cosmos, rings are not eternal crowns, but fleeting tiaras, destined to fade. Their impermanence makes them more poignant. Saturn's rings are not less beautiful because they will vanish. They are more so, precisely because their time is limited. They are the cherry blossoms of the solar system, breathtaking because they fall, snowflakes of ice that will one day melt into Saturn's skies. Cassini's final dive into Saturn in 2017 dramatized this impermanence. As the spacecraft plunged into the atmosphere, it carried with it the story of rings, that they are temporary, fragile, rain falling into a giant's clouds. Cassini died as Saturn's rings will die, transformed into atmosphere, lost but remembered. The mission ended, but it revealed the lesson of rings, that beauty is not permanence but transience. For planetary science, impermanence is a challenge. To study rings is to study them while they last. Each observation is a snapshot of a changing system. Saturn's rings are already eroding. Neptune's arcs may vanish before another spacecraft arrives. Even now, the solar system is changing, and its artworks shift with time. Rings remind us that astronomy is not about eternal objects, but evolving systems. They are not monuments of stone, but sculptures of snow and dust, shaped and reshaped by forces that never stop. Philosophically, impermanence is not despair but perspective. Rings show us that nothing in the universe is fixed, yet everything leaves traces. Saturn's rings may vanish, but their story will remain written in Saturn's moons, its atmosphere, its magnetic field. Future scientists will still read the evidence, just as geologists read vanished seas in Earth's rocks. Rings remind us that beauty is fleeting, but meaning endures. In the end, the transience of rings is their message. They are not eternal crowns, but temporary veils, not monuments, but performances. They remind us that the cosmos is dynamic, not static, and that we live in a privileged moment to see them. To look at Saturn now is to glimpse a masterpiece mid-performance, knowing that one day the stage will be empty. Rings are the solar system's most poignant artworks, grand, delicate, dazzling, and impermanent. From the moment Galileo first sketched Saturn with its strange ears in 1610, rings have fascinated not only scientists but human imagination. They are unlike anything else in the heavens. Planets, moons, and stars are points or disks of light. Rings are something different. Halos, crowns, adornments that turn planets into beings of myth. For centuries, Saturn's rings stood as an enigma, and even once their true nature was known, they retained their poetic allure. They are both physical structures of ice and dust and symbols, rich with meaning. Culturally, Saturn's rings became metaphors of majesty. In an age when planets were seen as wandering stars, Saturn's unique adornment marked it as special, a celestial monarch crowned in splendor. Early astronomers spoke of Saturn's appendages, or handles, groping for words to describe what they could not quite resolve. By the time Christian Huygens described them correctly as a thin, flat ring encircling the planet, they had already taken on symbolic weight. A planet, not merely existing, but adorned, chosen. To this day, Saturn is the ringed planet, its identity inseparable from its crown. But rings have also carried associations of liminality. They are boundaries, marking where the planet ends and space begins. Unlike moons, which orbit at a distance, rings hug the planet closely, forming a veil between world and void. This makes them metaphors for thresholds, between matter and emptiness, between permanence and impermanence, between order and chaos. In literature, Saturn's rings have been invoked as gateways, cosmic edges that frame the planet like the threshold of a temple. They are neither surface nor sky, but the liminal zone between. In art and philosophy, rings are symbols of eternity, but with irony. On Earth, rings, jewelry, halos, circles have long symbolized the infinite, the unbroken, the eternal. Wedding bands signify unending union. Halos signify sanctity. So it seemed fitting that Saturn bore a ring, a cosmic symbol of eternity. Yet modern science has revealed the irony. Saturn's rings are not eternal at all. They are transient, destined to vanish in hundreds of millions of years. This makes them even more powerful symbols. They embody the tension between what we imagine as eternal and what we know is fleeting. They are the universe's reminder that even the most beautiful crowns are temporary. The Cassini mission deepened this resonance. In its final orbits, Cassini measured ring rain, particles spiraling into Saturn's atmosphere, showing that the rings are actively disappearing. The poetry of impermanence became literal. Saturn's crown is falling, flake by flake, into its depths. When Cassini itself plunged into Saturn in 2017, it became part of that story. A human creation vanishing as the rings vanish, joining the cycle of impermanence. The mission ended, but its images remain, art within art, showing us the fragility of cosmic beauty. Philosophically, rings embody the theme of art in motion. They are not static structures, but dynamic systems, shaped by shepherd moons, resonances, and collisions. Saturn's F-ring braids and unbraids. Arcs at Neptune persist against the odds. Jupiter's dust halos are replenished by impacts. Rings are artworks in progress, constantly repainted. This makes them metaphors for life and history. Nothing is fixed, all is changing, yet the change itself is beautiful. The cosmos does not create permanent monuments, but ongoing performances. Rings also remind us of scale and perspective. To us, Saturn's rings are vast, spanning hundreds of thousands of kilometers. Yet they are only tens of meters thick, thinner than a sheet of paper compared to their breadth. To an observer standing within them, they would be more like a diffuse snowstorm than a solid band. Their grandeur is a trick of distance, their majesty an artifact of perspective. This too is symbolic. What seems monumental from afar may be fragile up close. What seems eternal may be fleeting. Rings humble us, reminding us that beauty is always a matter of scale. Culturally, rings have inspired artists and writers as symbols of the cosmic halo. In science fiction, they are often depicted as mysterious realms, with spacecraft threading their bands, or as metaphors for civilization itself, fragile, dynamic, luminous. Poets have likened them to wedding bands of the universe, or to crowns of kings, or to thresholds of divine presence. The association of rings with halos, with sanctity and transcendence, remains strong. Saturn, in this imagery, is not just a planet, but a crowned figure, a monarch of the outer solar system. Rings also echo in exoplanetary imagination. Artists envision giant exoplanets with massive ring systems, dwarfing Saturns, as potential homes for alien civilizations. These visions capture our longing for wonder. Rings are not only adornments, but stages, landscapes, places where imagination lands. The very idea of a ring system, vast, thin, fragile, speaks to our sense of the sublime. Beauty beyond practicality, grandeur without purpose, form that exists simply because the universe allows it. Ultimately, rings remind us that the universe is not only about function, but about form. Gravity, resonance, collision, these are mechanical forces, yet they create structures of staggering beauty. Saturn's rings are not needed for Saturn's existence. They serve no function for life or orbit. They are surplus beauty, gratuitous elegance. That is perhaps why they strike us so deeply. They suggest the cosmos is not a cold machine, but an artist, painting in ice and dust, creating beauty for no reason other than that it can. In closing, rings are cosmic symbols on multiple levels: crowns of majesty, thresholds of liminality, halos of eternity, metaphors of impermanence. They remind us that beauty can be both immense and fragile, that grandeur may last only for a season, that the universe is capable of art as well as mechanics. When we look at Saturn through a telescope, or gaze at Cassini's images of arcs, braids, and wakes, we are not only seeing physics, we are seeing meaning. We are seeing the cosmos reflected in art. And someday, when Saturn's rings have vanished, those meanings will remain. Future astronomers may read of them in ancient records, marveling that such a spectacle ever existed. For now, we are the witnesses, the generation lucky enough to see the solar system crowned. Rings, like all beauty, remind us not to take the present for granted. They are cosmic artworks, yes, but more than that, they are symbols of transience, majesty, and wonder. Magnetospheres and auroras. When we gaze at Jupiter, Saturn, Uranus, and Neptune through telescopes or spacecraft cameras, we see their clouds, storms, and rings. Yet these visible features are only half their story. Beneath the surfaces and veils of atmosphere, each of the giant planets hosts another, invisible realm, a magnetic field, generated deep within by powerful dynamos. These dynamos are not metaphors but real engines, the result of physics on immense scales. They transform internal energy into electromagnetic power, shaping space around them into magnetospheres that dwarf the planets themselves. To understand the giants as dynamos is to recognize them not as static spheres, but as cosmic machines, humming with invisible power. The basic principle of a dynamo is simple. When conductive material moves within a rotating body, it generates electric currents, which in turn produce a magnetic field. On Earth, this is achieved by molten iron moving in the outer core. On the gas giants, the situation is stranger and more exotic. Jupiter and Saturn are so massive that hydrogen, normally the lightest, most common gas in the universe, is compressed under immense pressure into a metallic form. This metallic hydrogen behaves like a liquid metal, conducting electricity and convecting in great rolling cells. Combined with rapid rotation, Jupiter spins once in just under 10 hours, Saturn in about 10.7. This moving metallic hydrogen becomes a dynamo of staggering scale. The result? Magnetic fields that make Earth's look modest. Jupiter's magnetic field is about 20,000 times stronger than Earth's, creating a magnetosphere so vast it would outshine the full moon in our sky if visible. Saturn's is weaker, but still immense, wrapping its rings and moons in a cocoon of magnetism. The ice giants, Uranus and Neptune, present an even stranger case. They lack the pressures to create vast oceans of metallic hydrogen. Instead, their dynamos arise from exotic ices, water, ammonia, and methane, compressed into unusual states. At extreme pressures and temperatures, water and ammonia can become superionic fluids, where hydrogen ions move through a lattice of oxygen or nitrogen atoms. These ionic oceans are conductive enough to drive dynamos. Unlike metallic hydrogen deep in Jupiter and Saturn, these dynamos are shallower, closer to the planet's surfaces. This difference explains why Uranus and Neptune have magnetic fields so peculiar, tilted, multipolar, and offset from the planet's centers. While Earth, Jupiter, and Saturn have relatively stable dipole fields, like giant bar magnets, Uranus's field is tilted by 59 degrees from its axis of rotation, and Neptune's by 47 degrees, with both offset far from their cores. Their magnetospheres wobble chaotically as the planets spin, producing unpredictable auroras and magnetic interactions. This diversity highlights one of the solar system's great lessons. There is no single blueprint for magnetism. The giants show us that dynamos can arise from very different materials and depths. Jupiter and Saturn are powered by the strangest metal in the cosmos, hydrogen turned metallic. Uranus and Neptune are powered by oceans of superionic water-ammonia mixtures, alien forms of matter we can only simulate in laboratories. Together, they reveal the dynamo as a universal principle, adaptable to many environments, a cosmic law that manifests differently depending on composition and pressure. Why does magnetism matter? Because these dynamos extend far beyond the planets. A magnetic field is not confined to the body that produces it. It projects outward, creating a magnetosphere, a region of space where charged particles are trapped and guided. Jupiter's magnetosphere, shaped by its enormous dynamo, is the largest structure in the solar system besides the Sun itself. If visible, it would stretch across the night sky, larger than the full moon by a factor of several times. Saturn's is smaller, but still engulfs its moons and rings. Uranus's and Neptune's magnetospheres are asymmetrical, tilted and lopsided, their boundaries constantly changing as they wobble, relative to the solar wind. These invisible structures dominate the space environments of their planets, influencing everything from auroras to radiation belts to the chemistry of moon's surfaces. The giant's dynamos also highlight a mystery of heat. Why do Jupiter and Saturn sustain such powerful convection to drive their dynamos? Both emit more heat than they receive from the Sun, suggesting ongoing contraction, or helium rain, deep within as energy sources. Uranus, however, radiates almost no excess heat, and its field is still strong, but bizarrely offset. Neptune radiates significant heat, fueling storms and a robust dynamo. The contrasts remind us that dynamos depend not only on composition, but also on thermal history, how a planet cools, contracts, and stirs its interior. The giants' magnetic differences are windows into their hidden interiors, telling us stories of formation and evolution we cannot see directly. Magnetic fields are not just local curiosities. They are templates for exoplanets. Many of the worlds discovered around other stars are Neptune-sized, ice giants, with likely ionic oceans beneath their atmospheres. If Uranus and Neptune's tilted, chaotic fields are typical, then many exoplanets may have magnetospheres unlike Earth's, shifting, multipolar, and unstable. Jupiter-sized exoplanets close to their stars, the so-called hot Jupiters, may have magnetic fields so strong they influence their stars directly, inducing auroras or radio emissions detectable from Earth. In this sense, the solar system's giants are not only themselves dynamos, but models of planetary magnetism across the galaxy. Culturally and philosophically, giant planet dynamos expand our sense of what is real. We tend to privilege what is visible: clouds, storms, rings. But the giants remind us that reality often lies in the unseen. Their magnetic fields are invisible to the eye, yet dwarf all visible features. They are not ornaments, but engines, shaping space itself. To study them is to glimpse the hidden skeletons of the cosmos, the frameworks of force upon which visible matter dances. For thousands of years, auroras were taken as signs from gods. Now we know they are the luminous edges of dynamos that hum deep within planets. The unseen has always fascinated us, and here it is made tangible. Philosophically, the giants as dynamos are metaphors of inward power. They remind us that greatness does not lie only in surfaces, but in inner movements. Beneath the clouds, invisible processes churn, metallic hydrogen swirling, ionic oceans shifting. From that hidden motion comes the force to light skies, trap radiation, and carve magnetospheres larger than the planets themselves. The lesson is profound, in worlds and in life. The unseen currents shape the greatest fields. If dynamos are the engines of the giants, then magnetospheres are their visible outputs, not in the sense of light, but in their influence on everything around them. A magnetosphere is more than a planetary bubble of magnetism. It is a vast domain where charged particles are trapped, accelerated, and redirected, creating both protection and peril. To cross the threshold of Jupiter's magnetosphere is to enter an environment as alien as any planetary surface. an invisible landscape of radiation and plasma shaped by gravity and magnetic force. The principle is simple. When a planet's magnetic field extends into space, it collides with the solar wind, the stream of charged particles flowing outward from the sun. Where the two meet, a boundary forms, the magnetopause, the edge of the magnetosphere. Inside this boundary, the planet's magnetic field dominates. Outside, the solar wind rules. Yet this is no static line. It ripples and shifts, pushed inward during solar storms, expanding outward during calm. Within, magnetic field lines act as invisible highways, guiding particles into belts and currents. The result is a realm of both order and chaos, a plasma world that is neither planet nor star, but a third kind of environment altogether. Earth offers a familiar model. Our Van Allen radiation belts trap electrons and protons, protecting Earth's surface from harmful radiation, but posing hazards to satellites and astronauts. Jupiter, however, elevates this to extremes. Its magnetosphere is the largest in the solar system, extending millions of kilometers into space. If visible to the human eye, it would appear larger than the full moon in Earth's night sky. Within this vast bubble lies a radiation environment so intense it would be instantly lethal to humans. Spacecraft must take special precautions when navigating near Jupiter, with instruments shielded and electronics hardened against bombardment. The Galileo orbiter, in the 1990s, frequently experienced glitches from radiation. Even Juno, a modern mission, has endured compromised instruments despite protective vaults. The intensity comes not only from the dynamo's strength, but from Io's contribution. Io's volcanoes spew sulfur and oxygen into space, filling Jupiter's magnetosphere with plasma. This material is trapped along magnetic field lines, accelerated and distributed into a donut-shaped region called the Io plasma torus. Here, radiation levels are unimaginably high, hundreds of times greater than in Earth's belts. The plasma torus is both a laboratory of extreme physics and a danger zone, a place where moons are constantly bombarded, their surfaces chemically altered by high-energy particles. Europa, for instance, shows signs of surface chemistry driven by radiation. Water ice on its surface is bombarded into oxygen, hydrogen, and peroxide, some of which may sink into its subsurface ocean. Thus, radiation, deadly to us, becomes part of a planetary cycle that could nurture life. Ganymede, too, endures constant interaction with the radiation environment, though it partially shields itself with its own intrinsic magnetic field. Io, meanwhile, is scarred and reshaped by both its volcanism and the plasma environment it feeds. In this way, Jupiter's magnetosphere is not merely a shield, but a world shaper, altering its moons and driving their evolution. Saturn's magnetosphere is gentler but still significant. Cassini revealed belts of trapped particles that interact strongly with the planet's rings and moons. Unlike Jupiter, where Io supplies sulfur and oxygen, Saturn's magnetosphere is fed by Enceladus. Its water-rich plumes inject vapor and ice particles, which become ionized and circulate along magnetic field lines. These ions not only contribute to Saturn's auroras, but also alter the chemistry of its space environment. Enceladus is thus not a passive moon, but a participant in Saturn's invisible realm, creating a system where ring, moon, and magnetosphere are interconnected. Even Titan, Saturn's largest moon, occasionally passes outside Saturn's magnetosphere, experiencing direct solar wind, a dynamic dance that shapes its thick atmosphere. Uranus and Neptune add complexity. Their offset, tilted fields create magnetospheres that are asymmetrical and unstable. As Uranus rotates on its side, its magnetosphere flaps like a broken umbrella, opening and closing, to the solar wind in unpredictable cycles. Charged particles are guided into belts that shift with each rotation, producing radiation zones that are chaotic and uneven. Neptune's magnetosphere, similarly tilted, twists and wobbles, creating a magnetotail that corkscrews through space. For spacecraft, these environments would be challenging to predict, full of sudden exposures and shifting hazards. Yet for science, they are opportunities to study plasma physics under conditions Earth cannot replicate. Chaos as a natural laboratory. Radiation belts are only one piece. Magnetospheres also shape ring systems. At Saturn, charged particles rain down onto the rings, influencing their chemistry and slowly eroding them. Cassini showed that ring rain, particles drawn inward along magnetic field lines, not only falls onto Saturn's atmosphere but also modulates its ionosphere, linking planet and rings in an electrical circuit. Jupiter's faint rings, supplied by dust from small moons, are also shaped by electromagnetic forces, with particles spiraling inward along magnetic lines. In each case, rings are not just ornaments, but participants in a magnetized system, sustained or eroded by invisible forces. Magnetospheres also act as cosmic shields. For planets with atmospheres, fields deflect solar wind that might otherwise strip them away. Earth's field protects our atmosphere from erosion. Mars, lacking a strong field, has lost much of its air to space. At the giants, atmospheres are massive enough that loss is less of a concern, but the principle is crucial for exoplanets. A strong magnetic field may mean the difference between a habitable world and a barren one, between oceans preserved and oceans lost. Thus, when we study Jupiter's magnetosphere or Saturn's belts, we are not only understanding the giants, we are learning what it takes for planets, and possibly life, to endure. The paradox of magnetospheres is that they are both protective and hostile. They shield atmospheres but trap radiation. They create auroras but also bombard moons. They are ecosystems of energy, where particles move in cycles of capture, acceleration, and loss. They remind us that space is not empty but alive, filled with invisible dynamics. The radiation belts around Jupiter, for example, may sterilize its immediate environment. Yet the chemistry they drive on Europa's surface may feed life below. The magnetosphere is thus a paradoxical womb, hostile on the outside, nurturing beneath. Culturally, magnetospheres are harder to romanticize than rings or storms, for they are invisible, yet their manifestations, auroras, have always carried wonder. For millennia, people have looked at shimmering curtains of light and seen omens, spirits, and signs from gods. Today we know those lights are born of invisible magnetospheres, converting charged particles into art. The link between unseen fields and visible beauty is itself symbolic. That which we cannot see often produces the most striking displays. Philosophically, magnetospheres embody the theme of the unseen shaping the scene. Planets appear as isolated spheres, but in reality they are surrounded by vast invisible structures that govern their fates. Radiation belts, alter moons, auroras, light skies, atmospheres endure or vanish depending on fields. To ignore magnetospheres is to miss half the story of planets. They are invisible realms, but no less real for that invisibility. They remind us that much of reality is hidden, its effects only visible in traces. Light shows in the sky, chemistry on a surface, gaps in a ring. In the end, magnetospheres are environments in their own right, as complex as surfaces or atmospheres. They are not just byproducts of dynamos, but living systems, shaping moons, rings, and habitability. To understand them is to see the solar system in full, with both its visible and invisible sides. To study them is to realize that space is not empty but structured, filled with unseen power. The giants, in their magnetospheres, are not only planets, but cosmic lighthouses, radiating invisible fields that sculpt their surroundings. If magnetospheres are invisible, auroras are their artistic signatures, painted on the skies where magnetic fields meet atmosphere. On Earth, we know them as the Aurora Borealis and Aurora Australis, curtains of green and red light rippling across polar skies, mesmerizing to behold. But Earth's auroras, beautiful though they are faint sketches compared to the grand canvases of the giant planets. On Jupiter and Saturn, auroras blaze constantly, far larger than Earth itself, visible not in gentle greens, but in powerful ultraviolet and infrared. They are not just lights. They are the solar system's greatest light shows, signals of cosmic energy transformed into beauty. On Earth, auroras are caused by charged particles from the solar wind spiraling along magnetic field lines and colliding with atmospheric gases. Oxygen glows green and red. Nitrogen glows blue and purple. The patterns shift and dance as Earth's magnetosphere channels the particles into ovals around the poles. Auroras wax during solar storms, fading in quieter times. They are transient, ephemeral, and tied to the sun's moods. For most of history, their causes were unknown. Cultures around the world saw them as portents, battles in the heavens, spirits of the dead, or flames of distant fires. Only modern science revealed the mechanism, magnetic fields converting invisible forces into visible light. Now expand that principle by factors of thousands, and you arrive at Jupiter. The king of planets has auroras so immense they dwarf our entire world, observed in ultraviolet by the Hubble Space Telescope, and in infrared by ground-based observatories. Jupiter's auroras are permanent, glowing ovals around each pole. They do not vanish when the solar wind weakens. Why? Because Jupiter's auroras are driven not only by the sun, but by Io, the volcanic moon. Io's eruptions spew sulfur and oxygen into space, feeding Jupiter's magnetosphere. As the planet's immense magnetic field whips around every 10 hours, it drags Io's plasma into a circuit, producing currents that slam into Jupiter's poles. The result is a steady, blazing aurora, the only permanent aurora in the solar system. In addition, solar wind events can intensify them, creating bursts of brightness and storms of light. Jupiter's auroras are also complex. In addition to the main ovals, they feature footprints, bright spots corresponding to its moons. Io, Europa, and Ganymede each create their own auroral signature, linked by magnetic flux tubes. These spots shift as the moons orbit, like moving beacons on a polar canvas. For Ganymede, the footprint even reveals the presence of a subsurface ocean, as the aurora wobbles in ways explained only by salt water beneath its crust. Thus, auroras are not just light shows, but diagnostics, tools that let us read the invisible. They carry messages from moons, magnetospheres, and interiors. Saturn's auroras are less steady, but equally magnificent. Observed by Cassini in ultraviolet and infrared, they form great ovals around the poles, shifting with the solar wind and with Saturn's rotation. They are less constant than Jupiter's, but more variable, flaring in storms, fading in calm, rippling like curtains. At times they appear as rings of light, circling the poles like crowns. At others as shifting arcs, like flames licking at the edge of darkness. Saturn's auroras are fed by both the solar wind and by Enceladus, whose plumes inject water into the magnetosphere. The chemistry of Saturn's auroras is different from Earth's, producing emissions in hydrogen's ultraviolet lines rather than oxygen's visible greens. Seen by human eyes, they might be ghostly violet or deep blue, colors beyond our familiar aurora palette. Uranus and Neptune, though less studied, also host auroras. Voyager 2 detected evidence of auroral activity at both, though their tilted offset magnetic fields make the displays irregular and unpredictable. The Hubble Space Telescope has since observed auroras at Uranus, glowing faintly in ultraviolet. Unlike Earth's and Jupiter's, they are not steady ovals, but scattered patches, sometimes appearing, sometimes vanishing, depending on how the tilted magnetosphere interacts with the solar wind. Neptune's auroras remain more elusive, glimpsed faintly, their dynamics still mysterious. These auroras, unstable and wandering, reflect the chaotic magnetospheres of the ice giants, where order is replaced by wobble and flux. What makes auroras so fascinating is that they are conversions of energy. Magnetic fields capture charged particles, accelerate them, and direct them into atmospheres. There, collisions with atoms release photons, light as a byproduct of violence. Auroras are the visible tips of invisible systems, beauty born of bombardment. They are reminders that the cosmos does not waste. Even processes that could be destructive create art. Jupiter's deadly radiation belts produce auroras of staggering scale. Saturn's magnetospheric circuits, fed by tiny Enceladus, produce rings of light. Earth's auroras, products of storms that could cripple satellites, become dances of color. Everywhere, danger and beauty are intertwined. For science, auroras are windows into magnetospheres. Observing their brightness and shape tells us how fields interact with the solar wind, how strong currents are, how moons contribute. At Jupiter, auroras reveal Io's plasma torus and Ganymede's hidden ocean. At Saturn, they map Enceladus's influence. At Uranus and Neptune, they reveal tilted fields and strange dynamics. For exoplanets, auroras may one day be the most detectable sign of magnetospheres. Telescopes may see flashes of radio or ultraviolet light from distant worlds, telling us not only that they have magnetic fields, but perhaps also that they host atmospheres or moons. Auroras could become beacons of habitability, cosmic lighthouses flashing across light years. Culturally, auroras remain symbols of awe. On Earth, they have inspired myths of spirits, battles, and omens. To see Jupiter's auroras blazing in ultraviolet across a world larger than Earth is to imagine what ancient peoples would have thought had they seen them, flames in the heavens too vast for comprehension. Saturn's auroras, violet crowns on a world already adorned with rings, add majesty to majesty. Uranus's and Neptune's auroras, faint and wandering, remind us of mystery, of the limits of what we can know from afar. In art and imagination, auroras are reminders of the link between the invisible and the visible, between force and form. Philosophically, auroras embody the idea of revelation. They are disclosures, signs of hidden systems made manifest. Without them, magnetospheres would be invisible, known only through instruments. With them, the invisible becomes visible. Physics becomes art. They remind us that the universe does not keep all its secrets. Sometimes it paints them in light, letting us glimpse the machinery of nature not as equations, but as beauty. In the end, auroras are the faces of magnetospheres. They are the visible smiles and frowns of invisible giants, the luminous masks of dynamos deep within. They are not trivial decorations, but essential expressions, telling us of plasma flows, solar storms, moon magnetosphere interactions. And beyond their science, they are simply beautiful. Curtains of light, crowns of fire, cosmic performances at the edge of the night. To study them is to study physics, but to see them is to feel wonder. They are reminders that the universe is not only structured, but sublime. When we think of moons, we imagine small companions circling their planets, bound by gravity, reflecting light. Yet at the giant planets, moons are not simply ornaments. They are electrical players, plasma suppliers, auroral artists. Each interacts with its parent's magnetic field, contributing mass, altering currents, or even generating their own. Moons do not merely orbit within magnetospheres, they help shape them. To grasp this is to realize that planetary magnetospheres are not solitary bubbles, but ecosystems, networks of exchange between planets, moons, and plasma. The most dramatic example is Io, Jupiter's innermost Galilean moon. Io is the most volcanically active body in the solar system, its surface constantly reshaped by sulfurous eruptions. These volcanoes eject plumes that rise hundreds of kilometers, hurling sulfur dioxide and other gases into space. In Io's tenuous gravity, much of this material escapes, becoming ionized by Jupiter's intense radiation. The result is a torus of plasma encircling Jupiter, the Io plasma torus. Trillions of tons of sulfur and oxygen swirl along magnetic field lines, feeding Jupiter's radiation belts and driving currents that connect Io directly to the planet. This connection is visible in Jupiter's auroras as the Io footprint, a bright spot where currents from Io's orbit funnel into Jupiter's poles. Each time Io circles Jupiter, its footprint shifts, leaving trails like brushstrokes on a polar canvas. Io is thus not only a volcanic world, but a generator, powering auroras and reshaping Jupiter's magnetosphere. Io's role goes further. The plasma it contributes rotates with Jupiter's powerful field, slowing the planet's magnetosphere slightly. To compensate, Jupiter drives currents that stretch millions of kilometers, accelerating particles and producing powerful radio emissions detectable from Earth. In this way, Io and Jupiter are locked in a cosmic circuit. Io supplies plasma, Jupiter supplies energy, the two exchange current. It is an electrical partnership unlike anything else in the solar system, a reminder that moons can be as significant as planets in shaping environments. If Io is the plasma supplier, Europa and Ganymede are subtler players, yet just as important. Europa, with its subsurface ocean, interacts constantly with Jupiter's magnetosphere. As charged particles bombard its icy surface, they split water molecules, creating a tenuous atmosphere of oxygen. Some of this sputtered oxygen feeds the magnetosphere. Some sinks into the ice, perhaps reaching the ocean below. Radiation, deadly to us, may thus provide oxidants for a hidden biosphere, driving a chemistry that could support life. Europa's role is not as dramatic as Io's, but it is profound. Its interaction with Jupiter's field may help sustain a potential habitat for alien life. Ganymede is even stranger. Larger than Mercury, Ganymede is the only moon known to generate its own intrinsic magnetic field. Voyager hinted at it. Galileo confirmed it. Ganymede's field creates a miniature magnetosphere inside Jupiter's vast one, the only known case of a moon with its own protective bubble. Interactions between these two fields are complex, producing auroras that flicker at Ganymede's poles. When Hubble observed those auroras, scientists noticed they wobbled less than expected, an effect best explained by the presence of a salty subsurface ocean. In other words, auroras on Ganymede revealed an ocean beneath its ice. This is science at its most poetic. Invisible magnetic currents, betraying the presence of hidden seas. Ganymede is thus not only a participant in Jupiter's magnetosphere, but also a reminder that magnetism can be a window to habitability. At Saturn, the key player is Enceladus. This small icy moon, only about 500 kilometers across, spews water vapor and ice grains from fissures near its south pole. Cassini flew through these plumes detecting water, salts, organics, even molecular hydrogen, a sign of hydrothermal activity beneath the ice. But Enceladus's influence goes beyond astrobiology. Its plumes feed Saturn's magnetosphere, creating a donut-shaped cloud of water-derived ions. These ions contribute to Saturn's auroras, linking the tiny moon to the giant planet's glowing poles. Like Io at Jupiter, Enceladus turns a local process, cryovolcanism, into a global one, reshaping the invisible realm. Without Enceladus, Saturn's magnetosphere would be poorer, dimmer, and less dynamic. Titan, Saturn's largest moon, also plays a role. With its thick atmosphere, Titan occasionally drifts outside Saturn's magnetosphere, exposed directly to the solar wind. When inside, it becomes part of Saturn's magnetic system, deflecting plasma, generating currents, and altering flow. Titan thus alternates between two environments, shielded and exposed, a cosmic duality that shapes its atmosphere. The study of Titan's interaction with Saturn's magnetosphere teaches us about how atmospheres endure or erode, lessons vital for exoplanets orbiting variable stars. At Uranus and Neptune, moon magnetosphere interactions are less well understood, yet evidence hints at similar dynamics. Neptune's Triton, with its nitrogen geysers, likely contributes plasma to Neptune's tilted magnetosphere. Uranus's moons, especially Miranda and Ariel, may show surface chemistry altered by bombardment. These worlds, less explored, await missions to reveal their magnetospheric roles. If history is a guide, we can expect surprises as dramatic as Io's plasma torus or Enceladus's plume-fed auroras. What unites all these cases is the realization that moons are not passive. They are active participants in magnetospheric ecosystems. Io, Europa, Ganymede, Enceladus, Titan, Triton. Each adds mass, drives currents, or generates fields. Magnetospheres are not planetary alone. They are planet-moon systems, electrical circuits of unimaginable scale. The giants and their moons are linked in invisible threads of plasma, currents that flow millions of kilometers, connecting worlds in ways gravity alone never could. Philosophically, this is profound. We are used to thinking of moons as satellites, dependents of their planets. But in magnetospheric terms, planets are as dependent on moons as moons on planets. Jupiter's auroras blaze, brighter because of Io. Saturn's auroras shimmer differently because of Enceladus. Ganymede reveals its ocean through its magnetic interaction. The giants are crowned not only with rings, but with invisible circuits woven by their moons. This interdependence speaks to a cosmic truth, that no world is alone. All are linked, exchanging matter and energy, shaping each other's environments. Culturally, the idea of moons as players enriches our imagination. Moons are no longer silent companions, but characters with voices in the cosmic symphony. Io, the fiery dancer. Europa, the hidden ocean. Ganymede, the shield-bearer. Enceladus, the fountain. Titan, the shrouded wanderer. Each leaves its mark not only on its planet, but on the magnetic skies themselves. Their roles remind us that beauty and meaning often come from interaction, from relationships rather than isolation. Planets are grand, but moons bring nuance, depth, and drama. In the end, the moons of the giants teach us that magnetospheres are ecosystems, not machines. They are sustained not only by planetary dynamos, but by contributions from companions. They are dialogues, circuits of matter and energy that tie planets and moons into single systems. To see Io's footprint in Jupiter's aurora, or Enceladus's ions lighting Saturn's skies, is to witness this dialogue made visible. It is a reminder that in the cosmos, as in life, relationships shape reality. The study of magnetospheres at Jupiter, Saturn, Uranus, and Neptune is not only about our solar system. These invisible realms are windows into the wider cosmos, where thousands of planets orbit other stars. In recent decades, astronomy has moved from asking if exoplanets exist to cataloguing them in the thousands. Among these discoveries are hot Jupiters, super-Earths, and countless Neptune-sized worlds. Yet as the catalogue grows, so too does a deeper question: which of these worlds could be habitable? And in that search, magnetic fields may be as crucial as atmospheres, oceans, or distance from the star. Magnetospheres as shields. On Earth, our magnetic field plays a quiet but critical role in sustaining life. By deflecting most of the solar wind, it prevents our atmosphere from being stripped away. Mars, lacking such a field, offers a stark contrast. Once it had rivers and perhaps oceans, but with its weak magnetism, the solar wind slowly eroded its air, leaving a thin, barren envelope. Venus, though shrouded in clouds, has no strong dynamo either. Its atmosphere survives due to sheer mass, but is stripped and reshaped by solar particles. From these examples, we see that a magnetic field is not merely accessory. It can be the difference between a living and a dead planet. For exoplanets, this principle is magnified. Around red dwarf stars, which make up the majority of stars in the galaxy, stellar winds and flares are intense. Planets in the habitable zone orbit close, enduring storms far stronger than Earth ever faces. Without magnetic protection, their atmospheres could be stripped in millions of years, a blink in cosmic time. Thus, a magnetic field may be one of the essential conditions for habitability. Studying the giant planets' magnetospheres shows us what strong fields can do, creating vast shields that not only deflect solar wind, but also create stable, structured environments in space. Hot Jupiters and stellar auroras. Among the first exoplanets discovered were hot Jupiters, gas giants orbiting extremely close to their stars. Their magnetospheres, compressed by fierce stellar winds, may interact directly with their stars, inducing auroras on the stellar surface itself. Astronomers have detected odd stellar brightenings and emissions that could be footprints of planetary magnetospheres, much like Io leaves a footprint in Jupiter's aurora. If confirmed, this would mean we can study exoplanetary fields, not by looking at the planets themselves, but by reading their effects on stars. Here, the lessons from Io and Jupiter are crucial. A small companion, through magnetic currents, can leave a luminous mark far away. Exomoons and invisible signatures. Just as moons in our solar system, Io, Europa, Ganymede, Enceladus, interact with magnetospheres to produce auroras and footprints, so too might exomoons betray their presence. Detecting moons directly is difficult, but auroral signatures could reveal them. A planet with a strong field might show periodic flashes or radio emissions tied to an orbiting moon, just as Io's footprint reveals itself at Jupiter. In this way, studying moons as magnetospheric players at home may lead us to discover moons abroad. Moons that could, like Europa or Enceladus, harbor oceans and perhaps life. Magnetospheres as clues to interiors. Magnetic fields also reveal planetary interiors. At Jupiter and Saturn, metallic hydrogen drives dynamos. At Uranus and Neptune, exotic ices do. Exoplanets come in many sizes, often larger than Neptune but smaller than Jupiter, the so-called mini-Neptunes and super-Earths. Do they generate fields? If so, what materials power their dynamos? Observing auroras or radio emissions from these worlds could tell us not only that they have fields, but also what lies within them. Magnetospheres become non-invasive probes, giving us clues to structure and composition without ever sending a spacecraft. Habitability beyond Earth. The ultimate lesson of magnetospheres is their link to habitability. For life to thrive, an atmosphere must endure. Oceans must be shielded from radiation, or if exposed, must be supplied with energy that can be used constructively. In our solar system, Jupiter's radiation sterilizes Europa's surface, but may also deliver oxidants to its ocean. Enceladus's plumes show that even a small moon can feed a giant magnetosphere. These interactions highlight that habitability is not a single condition, but a balance of shielding and exposure, nurture and challenge. Exoplanets and exomoons will likewise be shaped not only by their distance from a star, but by whether they are enmeshed in protective fields and magnetospheric circuits. For astronomers, auroras are particularly promising. While exoplanets themselves are faint, auroras are bright and energetic. Radio telescopes may one day detect auroral emissions from distant worlds, confirming the presence of fields. Already, hints of such signals have been reported, though not yet confirmed. The search continues, driven by the idea that auroras may be the most visible markers of invisible dynamos across the galaxy. The philosophy of invisible shields. Culturally, the notion of magnetospheres resonates as a metaphor of unseen protection. Earth's field is invisible to us, yet without it, we would not be here. The giants show us the grandeur of such shields on scales beyond comprehension. Jupiter's magnetosphere larger than the Sun itself. Saturn's linking rings and moons in circuits of plasma. To imagine exoplanets with such shields is to imagine invisible guardians, fields shaping the destiny of worlds. The poetry of magnetospheres lies in their paradox, unseen yet decisive, intangible yet vital. Philosophically, they remind us that life depends not only on what we see, oceans, atmospheres, warmth, but also on what we do not. Protection, structure, cycles of energy, these are invisible, but they sustain possibility. In this way, studying magnetospheres is more than physics. It is meditation on the conditions that allow life to persist in a hostile universe. From the Ioplasma torus to Saturn's auroral ovals, from Uranus's tilted chaos to Neptune's wobbly arcs, magnetospheres show us that planets are more than spheres. They are engines, shields, and artists of light. They trap, they protect, they create beauty. And as we look outward to exoplanets, magnetospheres become beacons, signs that worlds are active, shielded, perhaps habitable. In auroras shimmering across alien skies, we may one day see not only physics, but the first hints of life. In the grand search for habitability, magnetospheres remind us that the invisible is as important as the visible. They are the hidden scaffolding of worlds, the guardians of atmospheres, the artists of light. To study them is to expand our imagination, to recognize that every world has an unseen side, and that life itself may depend on the silent hum of a dynamo deep within. Jupiter has long stood in human imagination as the king of planets, its size and brilliance dominating the night sky. Yet its importance goes far beyond appearances. Jupiter is not just the largest planet in the solar system, it is also its gravitational gatekeeper. With a mass more than twice that of all the other planets combined, it exerts a gravitational influence that shapes the orbits of asteroids, comets, and even the smaller planets. For Earth, this influence has been a double-edged sword. Jupiter has both protected our fragile biosphere from catastrophic bombardments and, at times, acted as a cosmic sniper, sending deadly projectiles our way. The protective role is easy to imagine. Without Jupiter, Earth might still be enduring the kind of relentless bombardment that scarred the Moon with craters billions of years ago. Jupiter's immense gravity acts as a vacuum cleaner of the solar system, capturing comets that stray too close, deflecting them into harmless orbits, or swallowing them whole. The most dramatic demonstration came in 1994, when comet Shoemaker-Levy 9, torn into fragments by Jupiter's tides, slammed into the planet's atmosphere. The impacts released energies equivalent to millions of nuclear bombs. leaving Earth-sized scars in the Jovian clouds. Had Jupiter not been there, those fragments might have been on trajectories toward the inner planets, threatening Earth. Shoemaker-Levy 9 was a reminder that the solar system remains a shooting gallery, and that Jupiter often stands as our shield. But Jupiter's role is not purely benevolent. Its gravity can also act as a slingshot, hurling objects inward toward Earth rather than away. Many asteroids in the main belt are trapped in resonances with Jupiter, where its regular tugs destabilize their orbits over millions of years, sending some hurtling toward the inner solar system. Likewise, Jupiter can perturb comets from the distant Oort cloud, nudging them inward on long, looping paths. Without Jupiter, fewer of these would find their way into Earth's neighborhood. This makes Jupiter both guardian and sniper, a cosmic force that can protect or endanger, depending on circumstance. The debate over Jupiter's role in Earth's history has been lively among scientists. Some models suggest that without Jupiter, Earth would have suffered too many catastrophic impacts to sustain long-term habitability. Others argue that Jupiter has actually increased the flux of certain kinds of dangerous objects, like asteroids from resonant regions. In truth, the story is nuanced. Jupiter likely protected Earth from the most devastating cometary bombardments, while simultaneously sending a steady rain of smaller bodies inward. Paradoxically, this may have been essential for life. Early Earth needed impacts to deliver water and organic materials, but not so many that its surface was sterilized. Jupiter's dual role, both reducing the worst impacts and providing a manageable flux of smaller ones, may have been the perfect balance for a habitable world. This balance is written into the very architecture of the solar system. The asteroid belt, for instance, is not a failed planet, but a region sculpted by Jupiter's resonances. Its gravity prevented material from coalescing, leaving behind a population of rocky bodies that occasionally stray toward Earth. Similarly, the distribution of comets in the Kuiper belt and Oort cloud reflects Jupiter's gravitational history, scattering icy bodies outward during the planet's early migration. Jupiter is not a passive neighbor, but an architect, having shaped the traffic of small bodies that define Earth's risk and resource environment. The metaphor of guardian and sniper captures this duality. Like a watchful protector, Jupiter intercepts many cosmic threats, saving Earth from impacts that could erase civilizations or sterilize the biosphere. But, like a sniper hidden on the ridge, it also launches attacks. Not intentionally, but as a byproduct of its gravitational might. To live on Earth is to live under the shadow of Jupiter's double-edged presence, shielded by its mass, yet also vulnerable to its aim. Culturally, this duality resonates. Ancient civilizations saw Jupiter, Zeus to the Greeks, Jove to the Romans, as a ruler, a wielder of thunderbolts, both benevolent and wrathful. In this mythology, we sense an echo of its real role, a cosmic king with power to protect or to destroy. The impact scars on Jupiter's clouds after Shoemaker-Levy 9 looked like thunderbolts made manifest, celestial wounds from a planetary god. To imagine those impacts hitting Earth is to feel awe at Jupiter's guardianship, and humility at its potential to unleash chaos. Scientifically, Jupiter's role continues to be studied through simulations and models. Computer experiments show that giant planets in other systems could play similar roles, shaping the destinies of terrestrial planets. Some systems may lack such protectors, leaving their Earth-like worlds exposed to lethal bombardment. Others may have giants too close in, destabilizing habitable zones. Our own Jupiter, at just the right distance, may be one of the rarest kinds of planetary arrangements, a cosmic coincidence that made Earth possible. Philosophically, this raises profound questions. Is life common in the universe, Or is it rare because it requires such delicate balances? To have a habitable planet, do you also need a Jupiter? Massive enough to shield, distant enough not to disrupt, placed just right to deliver water and organics without overdoing destruction. If so, our existence depends not only on Earth's qualities, but also on Jupiter's, making it one of the most important players in the story of life. In the end, Jupiter is not simply a distant giant. It is Earth's unseen partner, a planetary bodyguard and occasional threat. Its gravity has sculpted the solar system's architecture, altered Earth's bombardment history, and perhaps made habitability itself possible. To understand Jupiter as guardian and sniper is to see it not as an isolated planet, but as a world builder, an architect of Earth's destiny. Without it, we might not be here at all. When we think about Earth as a habitable world, we often focus on its comfortable distance from the Sun, its atmosphere rich in oxygen, and its dynamic geology. Yet one of the most important ingredients for life, liquid water, was not guaranteed at Earth's birth. In fact, the early Earth formed under conditions that should have left it dry, a parched rock scorched by the sun. That our planet today is covered by oceans is a cosmic mystery, and one in which the giant planets played a decisive role. Without them, Earth might never have become a blue world, and life as we know it might never have emerged. The puzzle begins with the frost line, the invisible boundary in the early solar system where temperatures were low enough for water ice to condense. This boundary lay far beyond Earth's orbit, somewhere between Mars and Jupiter. Inside the frost line, materials were mostly dry rock and metal. Outside, ices and volatile compounds could survive. Earth, forming well inside this line, should have been largely devoid of water. Yet today, 70% of its surface is ocean, and water permeates its interior. Where did it come from? The prevailing answer: it was delivered. And giant planets were the couriers. During the chaotic early years of the solar system, Jupiter and Saturn did not sit placidly in their current orbits. According to the Grand Tack hypothesis, Jupiter first migrated inward, approaching as close as Mars's orbit, before reversing course and moving outward again when Saturn formed and entered resonance with it. This migration scattered icy planetesimals, the building blocks of comets and asteroids, inward toward the inner solar system. Many crashed into Earth and its siblings, delivering water and other volatiles. In this view, Earth's oceans are a direct result of Jupiter's wanderings. Without that gravitational stirring, the inner solar system might have remained dry, its planets barren stones circling the Sun. Evidence for this delivery comes from isotopic analysis. Scientists compare the ratio of deuterium to hydrogen, D/H, in Earth's oceans to that in comets and meteorites. Many comets have higher D over H ratios, suggesting they are not the main source. But certain asteroids, specifically carbonaceous chondrites, have DH ratios close to Earth's. These primitive bodies, rich in water and organic compounds, likely originated in the outer solar system and were flung inward by Jupiter and Saturn's gravitational chaos. Their impacts seeded Earth with water and the basic ingredients of life. In effect, Earth's oceans are a gift from asteroids. Asteroids placed on delivery routes by the gas giants. But water was not the only cargo. Carbonaceous chondrites contain a treasure trove of organic molecules, including amino acids, the building blocks of proteins. Laboratory analysis of meteorites, like the Murchison meteorite, which fell in Australia in 1969, revealed a catalogue of complex organic chemistry. These molecules formed naturally in the cold, radiation-bathed environments of space, then hitched rides to Earth on asteroids and comets. The giants, by stirring and scattering these bodies, ensured that the inner planets received regular doses of prebiotic ingredients. Thus, the seeds of life may not have originated on Earth at all, but were delivered by a cosmic supply chain, orchestrated by Jupiter and its kin. This paints a picture of giant planets not just as guardians or snipers, but as gardeners. Their gravitational sweeps distributed water and organics into the inner solar system, watering young Earth and fertilizing it with the raw materials of biology. Life's first chemistry may have begun in impact craters filled with melted water and organics, gifts from icy bodies redirected by giant planets. The same impacts that scarred Earth may have also planted the conditions for life to flourish. Of course, impacts were a double-edged sword. Too many could sterilize a planet, boiling away oceans as quickly as they were delivered. Earth's early history included a violent period known as the Late Heavy Bombardment, around 4 billion years ago, when impacts were frequent and colossal. It was during this time that the Moon's great basins formed, and Earth endured similar blows. Yet even in this violence, balance prevailed. The bombardment may have repeatedly reset the surface, but it also ensured abundant delivery of water and organics. Once the fury subsided, Earth was left with oceans and chemistry poised for life. Again, Jupiter's role was central. Its gravitational stirring was the catalyst of bombardment, and thus of delivery. Philosophically, this story redefines catastrophe. We often think of impacts as destructive, as extinction events like the one that ended the age of the dinosaurs. Yet impacts were also creative, the bringers of oceans, atmosphere, and organics. Jupiter and Saturn, by orchestrating these collisions, were not merely architects of chaos, but midwives of life. Without them, Earth might have been a sterile rock, its surface dry, its chemistry inert. Instead, we live on a world where water cycles, where carbon builds life, where oceans cradle ecosystems, all because the giants stirred the pot. The lesson extends to exoplanets. If Earth needed giants to deliver water, what of other systems? A terrestrial planet in a habitable zone may be dry unless a gas giant orbits farther out, scattering icy bodies inward. Conversely, if a giant orbits too close, it may prevent terrestrial planets from forming at all. Thus, the presence and placement of gas giants may determine not only whether a system has Earth-like planets, but also whether those planets are wet and alive. In searching for habitable worlds, astronomers now consider not just the size and orbit of Earth-like planets, but the architecture of their entire system. A habitable Earth may require a distant Jupiter as much as a sun. Culturally, this story adds a poetic twist. Humanity often sees water as sacred, life-giving, the essence of vitality. To know that Earth's water is not wholly Earth's, but a gift from wandering asteroids shepherded by Jupiter, enriches that sense of sacredness. Every glass of water, every ocean wave, every raindrop carries within it the memory of cosmic delivery. We drink the remnants of ancient asteroids. We swim in oceans seeded by giants. Our very existence is tied to the restless migrations of planets billions of years ago. Philosophically, it reminds us of interconnection. Earth is not an isolated miracle, but part of a larger cosmic choreography. Jupiter's migration, Saturn's resonance, asteroid belts, comet clouds, all contributed to Earth's story. Life is not only a product of Earth's conditions, but of the entire solar system's dynamics. We are the children, not just of Earth, but of Jupiter, Saturn, and the icy wanderers they guided inward. To recognize this is to expand our sense of origin. We are not simply Earthlings, but solar system beings, woven from materials and forces spanning billions of kilometers. In the end, the giants' role in delivering water and organics is perhaps their most profound contribution to Earth's habitability. They were not passive backdrops, but active participants, scattering the seeds of oceans and life. Without them, Earth might have remained a desert, a barren world circling a star. Instead, We live on a planet of rivers, seas, and forests, where chemistry blossomed into consciousness. In every drop of water and every strand of DNA, there is a trace of Jupiter's gravity, Saturn's resonance, and the chaotic ballet of early solar system migration. The giants are not distant curiosities. They are the gardeners of Earth. When we think of planets, we tend to imagine them as solitary spheres circling the Sun. Earth has a single moon, Mars 2 tiny companions, Mercury and Venus none. In this scheme, moons seem secondary, mere attendants, smaller bodies in the shadows of planets. Yet the giant planets tell a different story. They are not only worlds themselves, but creators of systems, each with dozens of moons ranging from asteroid-sized fragments to full-fledged worlds larger than Mercury. These moons are not afterthoughts. They are secondary planets, miniature worlds in their own right, shaped by the giants' gravity and magnetism. To study them is to realize that the solar system is not one system, but many. A family of planets and subfamilies of moons, each with its own dynamics, geology, and potential for life. Nowhere is this clearer than at Jupiter. Its 4 Galilean moons, Io, Europa, Ganymede, and Callisto, form a hierarchy as rich and varied as the planets themselves. Io is a volcanic hellscape, its surface a churn of lava and sulfur. Europa is an ocean world, its icy crust concealing a global sea of liquid water. Ganymede is the largest moon in the solar system, bigger than Mercury, with a magnetic field and evidence of a deep ocean. Callisto, heavily cratered, is an ancient relic, perhaps with a salty ocean beneath its crust. These are not inert rocks, but worlds with atmospheres, oceans, magnetic fields, and geological activity. They are secondary planets in orbit around a primary one, a miniature solar system held in Jupiter's grasp. Saturn's system is equally rich, if more enigmatic. Titan, larger than Mercury, has a thick nitrogen atmosphere, lakes and seas of liquid methane, and a methane cycle paralleling Earth's water cycle. Enceladus, though small, spews plumes of water and organics into space, evidence of a subsurface ocean with hydrothermal activity. Mimas, Rhea, Dione, Iapetus, each has quirks, from strange surface features to possible hidden oceans. Together, they form a network of worlds diverse enough to mirror an entire planetary system. Titan alone would be enough to merit study as a planet, yet it orbits as a moon. This inversion challenges our categories. What is a moon? What is a planet? If moons can be so planet-like. Neptune contributes its own jewel. Triton, a captured Kuiper belt object retrograding around the planet. With nitrogen geysers, a young surface, and the possibility of a hidden ocean, Triton is more dynamic than Pluto, the world it resembles. Uranus's moons, though less explored, also hold secrets. Miranda's bizarre patchwork surface, Ariel's hints of past cryovolcanism, Titania and Oberon's scarred terrains. These moons are not passive companions, but active worlds. Their surfaces and interiors shaped by tidal forces, resonances and magnetospheric interactions. They are laboratories of geology and astrobiology in miniature. What makes these moons so compelling is that they are products of the giants. Without Jupiter, Saturn, Uranus, and Neptune, these secondary worlds would not exist. The giants' massive gravity provided the disks of gas and dust from which moons accreted, just as the sun's disk gave birth to planets. In this sense, giant planets are planet makers twice over. First, they sculpt the solar system, influencing the fates of Earth and Mars. Then, they build their own families of moons, each a world unto itself. To see the Galilean moons is to see the solar system writ small. Volcanism, oceans, magnetism, ancient craters, a microcosm of planetary diversity. These secondary worlds also remind us that habitability is not confined to planets. In fact, some of the most promising habitats for life in the solar system are moons. Europa's subsurface ocean, warmed by tidal heating, may host hydrothermal vents and ecosystems like those on Earth's seafloor. Enceladus's plumes already carry organics, salts, and hydrogen, the ingredients of life. Titan's lakes and seas, though composed of methane, may host exotic chemistries that could parallel biology. Ganymede's hidden ocean, protected by ice and perhaps salted, may be another cradle of habitability. Even Callisto and Triton, once thought barren, may conceal oceans beneath their crusts. In total, the moons of the giants offer more potential liquid water than Earth does, hidden beneath kilometers of ice. If life is common in the universe, it may be more likely to emerge on moons than on planets. The giants thus expand our view of what a habitable system looks like. Earth is habitable because of its distance from the sun and its water. But moons like Europa are habitable because of tidal heating, magnetic shielding, and internal chemistry. Habitability is not only about sunlight, but also about energy in hidden forms. The giants, by locking moons into resonances and pumping them with tidal forces, provide such energy. Without Jupiter, Europa would be frozen solid. Without Saturn, Enceladus would be inert. The giants sustain worlds as much as they build them. Philosophically, this transforms our idea of worlds. A planet is not only a solitary sphere, but a system. Jupiter is not just Jupiter, but Jupiter, plus dozens of moons, each an environment. Saturn is not Saturn alone, but Saturn plus Titan, Enceladus, Iapetus, and others. To think of these planets as single objects is to miss their multiplicity. They are planetary families, microcosms within the macrocosm. Earth seems lonely with its one moon. The giants are crowded archipelagos of worlds, rich in diversity, fertile with possibility. Culturally, the moons of the giants have inspired both myth and imagination. Europa and Ganymede, named for mythic figures loved by Zeus, now represent worlds that may harbor life. Titan, named for ancient gods, embodies a myth made literal, a moon that is itself like a planet. Triton, named for the sea god, is a world of geysers and hidden oceans. These names, chosen centuries ago, resonate anew as science reveals their realities. The myths live on, reshaped by discovery, turning old stories into new ones. In the end, the moons of the giants are reminders that world building is not limited to stars. The sun built the planets, but the giants built the moons. And those moons may be as important to the story of life as Earth itself. If one day we find life elsewhere in the solar system, it may not be on Mars or Venus, but beneath the ice of Europa or Enceladus, in Titan's methane lakes, or in Triton's subsurface sea. The giants, in creating these secondary worlds, may have built the stages on which the universe's next act of biology will unfold. If Europa and Enceladus stir our imagination as ocean worlds, and Ganymede as a hidden giant, then Titan compels us for a different reason. It is the only moon with a thick atmosphere, a world that mirrors Earth in uncanny ways, yet plays by completely different rules. Titan is a living paradox, familiar yet alien, Earth-like yet utterly strange. To study it is to glimpse what Earth might have been under different conditions, an alternate experiment in planetary habitability. Titan's atmosphere is its most striking feature. It is thick, dense, and primarily composed of nitrogen, just like Earth's. In fact, Titan's surface pressure is greater than ours, making it the only body in the solar system where a human could stand without a pressure suit, though they would need oxygen and protection from the cold. Beneath this orange haze lies a world where rivers, lakes, and seas exist, but they are not made of water. Instead, methane and ethane flow in cycles that mimic Earth's hydrological cycle. Methane evaporates, forms clouds, falls as rain, and carves channels. Vast seas like Kraken Mare stretch for hundreds of kilometers, complete with shorelines, islands, and waves. Titan is the only other place we know of where liquids are stable on the surface, making it an eerie twin of Earth. The differences, however, are profound. Titan is frigid, with surface temperatures around -180 degrees Celsius, -290 degrees Fahrenheit. Water here is rock-hard ice, forming mountains and bedrock. Methane and ethane take water's role, sculpting landscapes, eroding valleys, pooling in lakes. Sand dunes stretch across equatorial regions, but the grains are made of organic particles, not silica. In Titan's skies, sunlight filters through a haze of tholins, complex organic molecules formed when ultraviolet light breaks down methane and nitrogen. These tholins rain down, coating the surface in reddish-brown dust. To walk on Titan would be to stand on Earth's shadow world, familiar in form, alien in substance. The Cassini-Huygens mission transformed Titan from a mystery into a landscape we could imagine. In 2005, the European-built Huygens probe parachuted through Titan's clouds, recording winds, haze, and light, before landing on a frozen plain strewn with rounded ice pebbles. Its descent showed branching river channels, drainage basins, and a surface shaped by flowing liquid. Cassini, orbiting Saturn for over a decade, used radar to peer through Titan's haze, mapping lakes, seas, dunes, and mountains. It discovered rainfall, seasonal changes, and even possible waves on Titan's seas. These observations revealed Titan not as a static moon, but as a dynamic world, with weather, climate, and geology. A planet-like system in miniature. Beneath Titan's icy crust, evidence points to another ocean, this one of water mixed with ammonia. Gravity measurements and rotational wobble suggest a global liquid layer, kept warm by internal heat and possibly enriched by salts. If true, Titan is doubly fascinating. An Earth-like surface environment, alien but familiar, and a hidden water ocean, perhaps hospitable to life as we know it. Titan thus offers two laboratories of habitability, a methane-based surface world and a water-based subsurface one. Could Titan host life? That depends on how broadly we define it. On its surface, life would have to use methane as a solvent instead of water, and ethane or acetylene as energy sources. Some scientists speculate about methanogenic life, cells with membranes built from different chemistries, metabolism based on hydrocarbon reactions. In laboratory experiments, researchers have simulated Titan conditions and shown that cell-like structures could form in liquid methane. If such life exists, it would be utterly alien, based not on our biochemistry, but on an entirely different one. Beneath the crust, in the water ocean, life would be more familiar, microbial organisms feeding on hydrothermal activity, like those at Earth's seafloor vents. Titan may therefore represent not just one, but two experiments in life's possibility. Culturally, Titan stirs deep fascination. Writers and thinkers have imagined it as a future frontier, a place humans might explore with relative ease, thanks to its thick atmosphere and low gravity. Powered flight would be simple there. Wings could lift heavy loads. Balloons could drift across seas. Science fiction paints Titan as a frontier for colonists, a place where methane lakes are resources and alien chemistries are challenges to overcome. Titan has become a canvas for imagining alternate Earths, worlds where conditions diverged, but form remained similar. It is an echo of home, transformed. Philosophically, Titan challenges our definitions of habitability. For centuries, we equated life with Earth-like conditions. sunlight, water, oxygen. Titan asks us to think broader. What if methane can do what water does? What if life adapts not to Earth's warmth but to Titan's cold? It stretches our imagination, forcing us to ask whether life is universal in chemistry or flexible, able to use whatever environment offers. Titan's dual worlds, a methane surface and a water ocean, symbolize this tension. One is alien to us, the other familiar. Perhaps both could harbor life, reminding us that habitability is a spectrum, not a fixed point. Titan also forces reflection on Earth's uniqueness. If Titan is Earth's alternate experiment, it shows how delicate the conditions of habitability are. Move a world farther from the sun, cool it enough, and its water freezes, methane takes over. Titan demonstrates how easily chemistry can shift, creating landscapes familiar in shape but alien in substance. It reminds us that Earth's warmth is a rare gift, one that makes our oceans liquid, and our skies blue instead of orange. Titan is a mirror showing what might have been. An Earth colder, stranger, yet still alive with activity. In the broader architecture of the solar system, Titan exemplifies the giants as world builders. Saturn provided the gravity, the materials, the magnetic environment that allowed Titan to form and evolve. Without Saturn, Titan would not exist. And without Titan, we would not have this alternate laboratory of habitability, this reminder that worlds can follow parallel paths and arrive at different outcomes. Titan is Saturn's greatest gift. A moon that is also a planet, a world that reflects Earth and challenges it. In the end, Titan is more than a moon. It is a thought experiment made real, a place where rivers and seas exist in alien form, where chemistry dances to unfamiliar rhythms, where habitability takes a different shape. It is Earth's twin, in outline, but not in essence. A mirror held up by Saturn, to show us both our uniqueness and our possibilities. To explore Titan is to explore the question of life itself, not just whether it exists elsewhere, but what it could be if freed from the constraints of Earth's template. As we extend our gaze beyond the solar system, thousands of planets have come into view. We have discovered rocky super-Earths, scorching hot Jupiters, icy mini Neptunes, and entire families of worlds circling distant stars. Amid this astonishing variety, one truth becomes clear. The architecture of a planetary system matters as much as the properties of individual planets. It is not enough to find an Earth-sized world in the habitable zone. We must also ask, what giants orbit farther out? What forces have shaped this system's history? For as Earth's story shows, gas giants are not passive giants in the background. They are architects, shaping bombardments, delivering water, controlling stability, and determining whether habitable worlds can exist at all. The solar system provides the model. Jupiter, Saturn, Uranus, and Neptune sculpted the asteroid belt, scattered comets, delivered water and organics, and moderated bombardments. Without them, Earth might not have oceans, may have endured endless impacts, or perhaps may not have formed at all. The placement of Jupiter in particular, massive, distant, and relatively stable, has been decisive. It shielded us from excess cometary bombardment, but also supplied essential materials. It carved space into habitable niches rather than chaos. The giants did not simply coexist with Earth, they enabled it. Exoplanetary discoveries suggest this pattern may not be universal. Many systems lack Jupiter analogues, gas giants in wide circular orbits that shepherd without destroying. Instead, we see hot Jupiters, massive planets in orbits tighter than Mercury's, circling their stars in days. These worlds likely migrated inward from their birthplaces, disrupting or even destroying inner rocky planets along the way. A system dominated by a hot Jupiter may never host Earth-like worlds at all. If it does, their orbits may be unstable, climates chaotic. Hot Jupiters are striking examples of giants as anti-architects, destabilizing rather than protecting. Other systems show resonant chains of mini-Neptunes and super-Earths, packed tightly in orbits where their mutual gravity keeps them locked in rhythms. In such systems, bombardments may be constant, orbital stability fragile, water delivery uncertain. Still others appear barren of giants, with only small rocky worlds close to their stars. Without outer giants, the protective sweep may be absent, leaving any habitable zone planet exposed to constant cometary bombardment. Earth's long stability, billions of years without sterilizing events, may be a rare outcome, a product of just the right giant planet configuration. From this perspective, gas giants are gatekeepers of habitability. Their presence or absence, their distance from the star, their migration history, all determine the chances that an Earth-like planet can survive and thrive. An Earth in a system without giants may be perpetually bombarded. An Earth in a system with a hot Jupiter may never form at all. An Earth in a system with a distant, stable Jupiter analogue may flourish for billions of years. Thus, the question, "Are we alone?" cannot be separated from the question, "Do other stars have Jupiters?" Astronomers now search specifically for Jupiter analogues, gas giants in orbits of 5 to 10 astronomical units, distant enough not to disrupt inner planets, close enough to influence small body reservoirs. Such giants are difficult to detect because they orbit slowly, but they are vital for assessing habitability. A star with an Earth-sized planet in the habitable zone and a Jupiter analogue farther out may be the best candidate for life. The architecture, not just the planet, is the key. The lesson extends to moons. In the solar system, giant planets built habitable niches, not only by shaping Earth, but by creating habitable secondary worlds like Europa, Enceladus, and Titan. Exoplanet giants may do the same. A gas giant in a habitable zone could host moons warmed by tidal heating, shielded by magnetospheres, fertile with oceans. Some scientists argue that habitable moons may be more common than habitable planets. If so, then the giants are doubly important. Architects of habitable systems and creators of habitable worlds in their own orbits. Culturally, this vision is transformative. For centuries, humans imagined Earth as the center of habitability, the one oasis in a vast desert. Now we see Earth as the beneficiary of architecture on grand scales. Jupiter's placement, Saturn's resonance, cometary scattering, water delivery, all these factors made Earth possible. To imagine other worlds is to imagine other architectures, other balances of chaos and order, destruction and delivery. Life elsewhere may not only depend on the right planet, but on the right arrangement of giants. Philosophically, this is a humbling lesson. Life is not inevitable wherever a rocky planet exists in a habitable zone. It requires stability, shielding, water, organics, and time, all of which are shaped by giants. Earth's habitability is not simply Earth's achievement, but a gift of the larger system. We are products of architecture, children of not only Earth, but Jupiter, Saturn, and the migratory ballet of the early solar system. To search for life elsewhere is to search for systems where such ballets have also played out with the same delicate outcomes. In the end, the giants are not just planets. They are world builders, cosmic architects shaping destinies across billions of years. They decide whether rocky planets are wet or dry, battered or stable, sterile or fertile. They create secondary worlds, moons with oceans and atmospheres, that may host life independently of planets. They sculpt not only the fates of worlds, but the chances of life itself. In the solar system, They made Earth possible. Across the galaxy, they may determine whether other Earths exist at all. Lessons for exoplanets. In October 1995, astronomy experienced a revolution. Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi, just 50 light-years away. It was a giant, roughly half the mass of Jupiter, circling its star in only 4 days. The discovery stunned astronomers. According to every model of planet formation at the time, such a world should not exist. Giants like Jupiter were expected to form far from their stars, beyond the frost line, where ices could condense and provide enough mass for runaway gas accretion. Yet here was a hot Jupiter, a gas giant roasting in a tight orbit, closer than Mercury is to our Sun. The rules, it seemed, were wrong. This first detection opened a floodgate. In the decades since, thousands of exoplanets have been discovered, and hot Jupiters turned out not to be rare oddities. They were the low-hanging fruit, easy to detect, because their large masses tugged strongly on their stars, and their quick orbits produced frequent transits. But their abundance forced astronomers to confront a new reality. Planetary systems are wildly diverse. The solar system, with its distant gas giants and small inner rocky planets, was not a universal template, but perhaps an exception. The very existence of hot Jupiters demanded explanation. How could they form so close to their stars? The leading theory is migration. Gas giants likely form farther out, as theory predicted, but then gravitational interactions with the protoplanetary disk or with other planets send them spiraling inward. Some may even slingshot off other giants, landing in star-hugging orbits. In the process, they often destabilize smaller inner planets, sweeping them away. The discovery of hot Jupiters thus revealed a violent truth about planetary systems. They are not stable clockworks, but dynamic arenas where worlds migrate, collide, and sometimes perish. Beyond hot Jupiters, astronomers began finding a new class of worlds, super Neptunes and mini Neptunes. These terms refer to planets between Earth and Neptune in size and mass, often rich in volatiles. Some are scaled-up Neptunes, with thick hydrogen envelopes. Others are rocky super-Earths with deep atmospheres. What makes them remarkable is their abundance. They are the most common type of planet in the galaxy, yet absent from our solar system. This fact reshaped our sense of normal Earth, and Jupiter may not be typical. Instead, planets in the intermediate zone may be the galaxy's standard issue. Mini-Neptunes, in particular, blur the line between rocky and gaseous worlds. Some may have deep oceans under thick atmospheres, others hydrogen-rich envelopes that smother their surfaces. The Kepler mission revealed dozens of such planets in compact systems, orbiting close to their stars. Many exist in tightly packed resonances, resembling nothing in our solar system. Systems like TRAPPIST-1, with 7 rocky worlds around a cool red dwarf, show that variety is the rule, not the exception. These discoveries forced a shift in perspective. For centuries, humanity assumed the solar system was typical, that other stars would host familiar architectures. The reality is far stranger. Some stars host hot Jupiters grazing their surfaces. Others, mini-Neptunes in endless chains. Others, planets orbiting binary suns. Instead of one model, we now see a cosmic zoo, with diversity exceeding imagination. Yet in this diversity, lessons emerge. Hot Jupiters show us the power of migration, teaching us that planetary positions are not fixed, but dynamic. Mini-Neptunes show us that planetary formation produces outcomes Earth never did, perhaps due to Jupiter's disruptive influence. Super Neptunes show us that ice giants like Uranus and Neptune are not rare oddities, but key members of galactic families. By studying these exoplanets, we learn that our own solar system is not a template, but a case study. a single example of what planetary systems can become. The implications for habitability are profound. Hot Jupiters, by migrating inward, often destabilize habitable zones, stripping them of rocky worlds. Systems dominated by mini-Neptunes may have few Earth-like planets. Conversely, some systems may benefit from giants that remain in distant, stable orbits, much like our Jupiter. In this sense, our own system may be unusual, but unusually fortunate. Without hot Jupiters or disruptive migrations, Earth was left intact, in a stable orbit, long enough for life to flourish. Culturally, the discovery of hot Jupiters and mini-Neptunes was a shock akin to Copernicus's revelation that Earth was not the center of the universe. It overturned assumptions, replacing a comforting model with a stranger, richer reality. Instead of solar systems everywhere, we found alien architectures, bizarre and varied. Philosophically, it forced us to rethink normal. Perhaps there is no normal. Perhaps the universe is not populated by copies of our solar system, but by experiments. Each star a laboratory of different planetary possibilities. In the end, the age of discovery showed us that we live in a galaxy of possibilities. Hot Jupiters circling in days, super Neptunes dwarfing Earth, mini-Neptunes cloaked in haze, all challenge our imagination. Yet they also sharpen our understanding. By studying them, we can see our own system in context, learning what is rare, what is common, and what it takes for a world like Earth to exist. The discovery of hot Jupiters began with surprise, but it continues with insight. Every planet tells a story, and together they reveal a universe far richer than we ever dreamed. The discovery of hot Jupiters, super Neptunes, and mini-Neptunes gave us a dizzying array of planetary types. But to interpret them, we needed a foundation. Luckily, we already had a laboratory, our own solar system. For centuries, Jupiter, Saturn, Uranus, and Neptune have been our test cases. Objects close enough to study in detail, yet strange enough to stretch our theories. As exoplanets revealed their diversity, the giants of our system became Rosetta Stones, guides that helped decode what distant signals might mean. Take Jupiter. It is the archetypal gas giant, massive enough to dominate its planetary family, with a composition similar to the Sun. By studying Jupiter's structure, we learned how gas giants form. A solid core forms first. Then runaway accretion builds a massive envelope of hydrogen and helium. Its storms, belts, and great red spot show us how atmospheres behave when freed from solid surfaces, convecting on scales Earth cannot match. More importantly, Jupiter's magnetosphere, the largest structure in the solar system, demonstrates what happens when rotation, metallic hydrogen, and solar wind interact. When we see hints of magnetic interactions in exoplanet data, we use Jupiter as the yardstick. Jupiter also reminds us that gas giants are not isolated. Its moons, volcanic Io, oceanic Europa, massive Ganymede, and ancient Callisto, are worlds in themselves. Together they form a miniature solar system, rich in geology and chemistry. For exoplanet science, this is critical. A gas giant in the habitable zone may not be habitable itself, but its moons could be. Europa and Enceladus show us that subsurface oceans can exist, fed by tidal heating. Titan shows us that thick atmospheres can shroud moons as well as planets. Every time we imagine exomoons around a distant gas giant, we draw on these analogues. The lesson is simple. Gas giants are not barren. They are world builders. Saturn provides another template. If Jupiter is the archetypal gas giant, Saturn is the artist. Its rings, dazzling, dynamic, ephemeral, are unique in their grandeur, but also instructive. They show how gravitational resonances sculpt disks, how moons shepherd material, how collisions create beauty. When astronomers study protoplanetary disks around young stars, they often see gaps, arcs, and rings of dust. Saturn is our analogue, a natural laboratory for how structure emerges in orbiting material. Its moons add further lessons. Enceladus demonstrates that even tiny worlds can harbour oceans and geysers, sustained by tidal heating. Titan shows how methane can replace water in cycles of rain, rivers, and seas. Saturn, with its elegance and diversity, tells us to expect the unexpected in other systems. Uranus and Neptune, though less glamorous in popular culture, may be the most relevant for exoplanet science. The most common exoplanets are not Jupiters or Earths, but Neptune-sized worlds. They sit in a middle zone, too small to be gas giants, too large to be terrestrial. Uranus and Neptune, with their icy mantles of water, methane, and ammonia, are our only examples. Their offset magnetic fields, extreme winds, and stormy atmospheres remind us that these planets are complex, not mere ice balls. When we study mini-Neptunes and super-Earths around other stars, we rely on Uranus and Neptune to interpret what those planets might be like. Without them, we would have no benchmarks. Our giants also teach us about migration. The Grand Tack hypothesis, in which Jupiter moved inward then outward, reshaping the solar system, parallels theories of hot Jupiter migration. By studying the scars left in the asteroid belt and Kuiper belt, we see how giant planets sculpt small body populations. When we observe exoplanet systems with tightly packed planets or cleared-out gaps, we can read them in light of Jupiter's past. The giants remind us that orbits are not fixed, that planetary systems are dynamic over time. Even their atmospheres teach us. By probing Jupiter and Saturn with spectroscopy, we have learned to detect methane, ammonia, and water vapor at great distances. These techniques, refined at home, are now used on exoplanets. When the James Webb Space Telescope observes the transmission spectrum of a hot Jupiter's atmosphere, it is using methods perfected on our giants. Every band of methane or water we identify in an exoplanet's spectrum is grounded in lessons from Jupiter, Saturn, Uranus, and Neptune. Perhaps most importantly, our giants remind us of diversity within categories. Jupiter and Saturn are both gas giants, yet their densities, atmospheres, and magnetic fields differ greatly. Uranus and Neptune are both ice giants, yet their magnetic fields and heat balances diverge. This diversity warns us against oversimplification. When we classify an exoplanet as a hot Jupiter or warm Neptune, we must remember that categories hide complexity. Just as Jupiter is not Saturn and Uranus is not Neptune, no two exoplanets will be alike. Our system's variety is a preview of the galaxies. Culturally, the giants also serve as archetypes. Jupiter, the king; Saturn, the ringed artist; Uranus, the tilted eccentric; Neptune, the stormy wanderer. These archetypes enrich our imagination as we look outward. When astronomers name exoplanets, when writers describe alien systems, the images of our giants loom in the background. They are the mythic templates as well as the scientific ones. Philosophically, the giants ground us. Exoplanets are distant, detected as faint dips in starlight or tiny wobbles in spectra. They are abstractions, numbers on graphs. Our giants remind us they are real. They have clouds, storms, magnetospheres, moons, histories. By studying Jupiter and Saturn, Uranus and Neptune, we give flesh to exoplanets, turning abstractions into worlds we can imagine. They remind us that planets are not just data, but places. In the end, the giants of our solar system are more than local curiosities. They are guides, interpreters, teachers. They show us how to read the signals of distant worlds, how to understand migration, atmospheres, magnetism, and moons. As we discover more exoplanets, their lessons grow more valuable. We may never visit most of those worlds, but by knowing our giants, we can see them more clearly. In the giants, we find the keys to the galaxy. In the solar system, moons are not side nodes. They are volcanic furnaces, hidden oceans, methane weather worlds, secondary planets orbiting giants. If exoplanets have moons, then the number of potentially habitable worlds in the galaxy could multiply many times over. The hunt for exomoons, moons around planets orbiting other stars, is one of the most exciting quests in modern astronomy. Yet it is also among the hardest. Detecting a planet orbiting a star is already a challenge. Detecting a moon orbiting that planet is a feat of precision at the very limits of our technology. Still, tantalizing hints suggest that exomoons may be out there, waiting to rewrite our vision of habitable worlds. The case for exomoons begins with numbers. In our solar system, moons outnumber planets by a wide margin. Jupiter alone has more than 90. Saturn has over 80. Even smaller planets have companions. If such abundance is typical, then the galaxy should be filled with moons. Billions, perhaps trillions. Many may be sterile rocks, but others could be like Europa or Titan. Ocean worlds warmed by tidal heating, shielded by their planet's magnetospheres. If so, exomoons may be common habitats, perhaps more so than Earth-like planets themselves. To search for life, then, is also to search for moons. Detecting exomoons requires subtlety. The most common method of finding exoplanets is transits, when a planet passes in front of its star, dimming the light slightly. A moon could reveal itself in several ways. First, it could cause extra dips in brightness, a smaller transit overlapping the larger one. Second, it could produce transit timing variations, TTVS. The planet's transit would occur slightly earlier or later, depending on the moon's gravitational pull. Third, it could cause transit duration variations, TDVS, changing the length of the transit. By combining these clues, astronomers can infer the presence of a moon. But the signals are faint, buried in noise, and often ambiguous. Stars flicker, instruments wobble, and distinguishing moon from artifact is notoriously difficult. Despite the challenges, there have been intriguing hints. In 2017, astronomers reported possible evidence of a giant exomoon around the planet Kepler, 1625b, a Jupiter-sized world orbiting a Sun-like star 8,000 light-years away. The data suggested a Neptune-sized companion, a moon far larger than anything in our solar system. If confirmed, it would be the first exomoon discovery, and a startling one, since our moons are all much smaller. But the evidence is contested, with some attributing the signal to noise or data gaps. The search continues, with follow-up observations using the Hubble Space Telescope, and more recently, the James Webb Space Telescope. Whether Kepler 1625bi exists or not, the episode highlights both the promise and difficulty of the field. Future missions hold hope. TESS, Transiting Exoplanet Survey Satellite, already scanning nearby stars for planets, has the sensitivity to pick up moon-like signals in certain cases. JWST can follow up on candidates, probing atmospheres and confirming orbital dynamics. Further ahead, proposed missions with ultra-precise photometry may finally resolve the exomoon question. Some astronomers even propose hunting exomoons through their auroral signatures, as moons interacting with giant planet magnetospheres might produce detectable radio emissions. Just as Io's footprint marks Jupiter's aurora, exomoons might betray themselves in electromagnetic whispers across the cosmos. Why does this matter? Because moons broaden the horizons of habitability. A planet in the habitable zone of a star may be dry or hostile, but its moons, heated by tides, could be alive. In our solar system, Europa, Enceladus, Titan, and Ganymede are all candidates for habitability. None are planets. If exomoons are common, then habitable environments could be 10 times more numerous than habitable planets. The galaxy may be rich not in Earths but in Europas, in Titans, in Enceladus's orbiting distant Jupiters and Neptunes. The hunt for exomoons also forces us to expand our imagination. What might alien moons be like? Could there be super Europas, moons larger than Mars with oceans hundreds of kilometers deep? Could there be Titan-like moons with methane seas under orange skies? Could giant exomoons even be habitable on their surfaces, with atmospheres and climates of their own? Kepler's tantalizing hint of a Neptune-sized moon suggests possibilities beyond anything in our solar system. Nature may not limit moons to small sizes. It may build them as secondary planets in the fullest sense. Culturally, the search for exomoons has a mythic quality. For millennia, moons have been symbols of mystery, romance, and cycles. To imagine not just planets, but moons around other stars, is to enrich the cosmic stage with new characters. Alien skies where 2 or 3 moons rise, or worlds where habitable life orbits not stars directly, but giants. Exomoons are the stuff of science fiction come alive. Pandora from Avatar, Endor from Star Wars. Worlds of imagination now sought in reality. Philosophically, exomoons remind us of humility. We once thought habitability meant Earth clones. Then we realized Mars-like and Venus-like planets must be considered. Then ocean moons within our solar system expanded the picture further. Now, the search for exomoons extends the frontier again. Life may not orbit stars directly, but giants as secondary companions. The cosmos may be teeming with hidden havens in places we never thought to look. In the end, the hunt for exomoons is still in its infancy, but its promise is vast. Each method, each candidate, each debate brings us closer to an answer. If moons are as abundant in other systems as they are here, then the galaxy is not just full of planets, but populated by worlds upon worlds, satellites that are themselves centers of potential. The giants build these worlds, nurture them, and perhaps across light years, they carry life in their orbits. To find exomoons is not only to expand our planetary census, but to rewrite our concept of habitability itself. For centuries, astronomers defined habitability narrowly. A planet must orbit its star at the right distance for liquid water to exist on the surface. This region, the so-called habitable zone, is where starlight warms a planet enough to keep water from freezing, but not so much that it boils away. Earth sits comfortably in this zone. Mars teeters on its outer edge, and Venus lies just inside the inner edge. But the giant planet's moons, with their hidden seas and icy shells, force us to rethink this framework. They show us that habitability is not only about distance from a star, but about energy in all its forms. Consider Europa. Far beyond the Sun's traditional habitable zone, this small moon of Jupiter should be frozen solid. Its surface is indeed ice, but beneath lies a global ocean of liquid water, kept warm not by sunlight, but by tidal heating. As Europa orbits Jupiter, it is tugged and flexed by the giant planet's gravity, its shape stretched and squeezed. This flexing generates frictional heat within its interior, enough to maintain an ocean beneath the ice. Ganymede and Callisto may harbor similar oceans, though deeper and more insulated. Io, also heated by tides, demonstrates the extremes of this process, with its surface a volcanic inferno. Together, these moons show that tidal heating is a powerful source of energy, one that can make worlds habitable far from starlight. Enceladus, Saturn's tiny ocean moon, offers another case. Barely 500 kilometers across, it should be a frozen block. Yet geysers blast from its south pole, venting water vapor, ice and organics into space. Cassini's instruments revealed molecular hydrogen in the plumes, a sign of hydrothermal activity at the ocean floor. Here, in a world so small it cannot hold heat for long, tides provide the missing energy. Enceladus is proof that size and distance need not dictate habitability. What matters is whether gravity stirs the interior into warmth. Titan complicates the picture even further. With its methane seas and nitrogen atmosphere, it hosts a surface environment entirely alien to Earth. Yet beneath its icy crust may lie another hidden ocean of liquid water mixed with ammonia. Tidal flexing, along with residual heat from its formation, may keep it liquid. Thus, Titan may offer two laboratories of habitability, one methane-based at the surface, another water-based below. It is a reminder that habitability can take multiple forms, each enabled by forces beyond starlight. These lessons force us to expand the habitable zone. Instead of a narrow belt around stars, we must imagine a habitable archipelago, moons orbiting giants, each with its own source of energy. A gas giant in a distant orbit may host multiple habitable moons, each warmed by tides. In such systems, the habitable zone is not a single line, but a network, a family of worlds linked to their giant parent. This radically increases the number of possible habitats in the galaxy. If exomoons are common, then habitable worlds may be too, even in systems where no Earth-like planets exist. Tidal heating also works in concert with other factors. Moons in habitable zones around stars could combine stellar warmth with tidal warmth, creating especially fertile environments. A moon of a gas giant in the habitable zone might have surface water, subsurface oceans, and magnetospheric protection. Such a world could be richer in energy than Earth itself, a superhabitat with multiple niches for life. The giant's ability to generate tides and foster oceans thus multiplies possibilities, making life-friendly conditions not rare exceptions, but potentially common outcomes. But are these oceans truly habitable? Earth offers guidance. At our seafloor hydrothermal vents, life thrives without sunlight, feeding on chemical energy from the interaction of seawater and hot rock. Microbes cluster in mineral chimneys supported by hydrogen and sulfur compounds. Larger organisms, worms, clams, crabs, build ecosystems around them. If such life can exist on Earth, why not in Europa's ocean, where hydrothermal vents likely churn at the seafloor? Why not in Enceladus, where hydrogen is abundant? Life, at least microbial, may not require starlight at all. It may require only water, chemistry, and energy. Conditions tidal heating provides in abundance. Philosophically, this is transformative. It breaks the tyranny of the habitable zone, freeing life from the narrow strip of warmth around stars. Life may not be fragile, confined to thin bands, but stubborn, adaptable, thriving in hidden oceans beneath ice. It suggests the galaxy may teem with biospheres in places once dismissed as dead. The stars are no longer the sole fountains of life. Gravity itself becomes a life-giver, tides a source of warmth, moons as fertile as planets. Culturally, this idea resonates with myth. For ages, oceans symbolized mystery and depth. Now we realize that oceans may exist everywhere, hidden under ice across the solar system and beyond. To imagine alien seas beneath Europa or Enceladus is to evoke ancient images of hidden realms, underworlds where life waits unseen. The difference is that these oceans are not myths, but scientific possibilities, testable and within reach of future missions. The romance of the ocean merges with the rigor of science, expanding both imagination and knowledge. Practically, this expands the scope of our search. Instead of focusing only on Earth-sized planets in habitable zones, astronomers now consider gas giants and their moons. Future telescopes may look for exomoons showing signs of oceans, tidal heating, or atmospheres. In our own system, missions like Europa Clipper and Dragonfly to Titan will probe these questions directly. The giants' moons are not only targets for exploration, but templates for the galaxy, showing us what to look for elsewhere. In the end, the lesson is clear. Oceans are not rare. They are everywhere. They flow beneath Europa, Enceladus, Titan, Ganymede, and perhaps even Triton and Callisto. They are warmed not by sunlight, but by tides, chemistry, and hidden heat. They show us that habitability is broader than we imagined, more generous, more widespread. If life exists beyond Earth, it may be swimming not under a sun, but under an ice crust, in oceans kept alive by the pull of giants. When we look out into the galaxy, we see extraordinary diversity. There are planets larger than Jupiter, orbiting so close to their stars they glow with heat. Neptune circling in tight chains around dim red suns. Earth-sized worlds packed together in systems very unlike our own. Yet amid this variety, a pattern emerges. Gas giants are common, and they seem to play decisive roles in shaping their systems. To understand them, we turn back to the giants of our solar system. Jupiter, Saturn, Uranus, and Neptune are not just local curiosities. They are templates, archetypes we can use to interpret alien worlds. Each giant carries a lesson. Jupiter is the gravitational king, its mass sculpting the asteroid belt, deflecting comets, and shielding Earth. In exoplanetary terms, Jupiter represents the class of cold Jupiters, massive planets orbiting far from their stars, often stabilizing systems and allowing habitable planets to endure. When astronomers find a distant gas giant, they often ask, is it playing the same role as Jupiter, protecting inner Earths? Without such guardians, habitability may falter. Jupiter thus becomes the model for how giants can be both destroyers and sustainers of life. Saturn teaches us about elegance and subtlety. Its rings, shepherded by moons, provide a natural laboratory for processes we see in protoplanetary disks around young stars. The gaps and arcs in those disks mirror Saturn's rings, reminding us that planets and moons sculpt material everywhere. Saturn's moon Titan adds another lesson. Gas giants can spawn habitable moons, alternate experiments in climate and chemistry. An exoplanet Saturn analog in a habitable zone could host Titan-like moons, making such systems especially promising for life. Saturn shows us that giants are not just gravitational forces, but also creators of secondary worlds. Uranus is the eccentric, tilted on its side, with a magnetic field offset and lopsided. Its strangeness warns us that giants can be unpredictable, shaped by ancient impacts or unusual chemistry. For exoplanets, Uranus represents the class of sub-Neptunes and ice giants, which are among the most common worlds in the galaxy. By studying Uranus's atmosphere, magnetosphere, and moons, we glimpse what countless exoplanets may be like, worlds of exotic ices, tilted fields, and unexpected dynamics. Uranus is our reminder not to assume order, but to expect the strange. Neptune is the storm king, its winds faster than sound, its magnetosphere twisting in chaos, its moon, Triton retrograde and active. It represents dynamism, turbulence, and capture. Exoplanet Neptunes may likewise have moons captured from their system's outer regions, or atmospheres shaped by intense winds. Neptune also shows us that even small giants can sculpt entire systems. It shaped the Kuiper belt, scattering icy bodies outward. In other systems, Neptunes may be the dominant sculptors, determining the fate of smaller planets. Neptune is the archetype of the unexpected, the evidence that small giants wield power far beyond their size. Together, these four provide a taxonomy. Jupiter as the stabilizer, Saturn as the creator, Uranus as the eccentric, Neptune as the turbulent. They give us archetypes for interpreting exoplanet giants, whose faint signals often tell us little more than size, mass, and orbit. By mapping alien giants onto our four templates, we can begin to imagine their roles. Are they guardians, sculptors, eccentrics, or storm kings? Our solar system becomes a key, unlocking the hidden stories of systems we cannot yet visit. The giants also serve as templates for habitability. They teach us that life may not orbit stars directly, but giants. Their moons may be the true havens, Europas, Enceladus's, Titans scattered across the galaxy. A giant in a habitable zone may not be habitable itself, but it may host a family of habitable moons. If moons are as common elsewhere as they are here, then gas giants may be the true cradles of life in the universe. This reframes the search. Instead of asking only where Earth-like planets exist, we must ask where giants orbit, for their moons may be more numerous and more promising. Philosophically, this casts gas giants as cosmic architects. They are not just planets, but system builders. They deliver water and organics, shield inner worlds, destabilize or stabilize orbits, and create moons that may host oceans. They are engines of habitability, deciding whether smaller worlds can thrive. In our solar system, they made Earth possible. In the galaxy, they may determine whether other Earths exist at all. Culturally, the giants enrich our imagination. In myth, Jupiter, Zeus, was king of the gods, Saturn, Cronus, the ruler of time, Uranus, the primal sky, Neptune, the sea's storm. These archetypes resonate with their planetary realities. Jupiter, the kingly protector, Saturn, the time-worn ring-bearer, Uranus, the tilted sky, Neptune, the stormy sea. As we apply these archetypes to exoplanets, we carry not only science but story, weaving myth into exploration. Alien giants will need new names, but their roles may echo our own myths. Guardians, destroyers, creators, eccentrics, kings. In the end, gas giants are not just part of planetary systems. They are templates for understanding the universe. They show us how systems form, how they evolve, how life may arise. Every exoplanet giant we discover, hot or cold, close or far, adds another variant, another experiment. But the keys to interpretation remain at home, in the four giants orbiting our sun. They are the Rosetta Stones, the archetypes, the templates of possibility. By knowing them, we can begin to know the galaxy. For all the progress humanity has made in exploring the solar system, the gas and ice giants remain in many ways unfinished business. Voyager 1 and 2 gave us breathtaking flybys in the late 1970s and 1980s, showing us Jupiter's volcanic moon, Io, Saturn's rings in intricate detail, Uranus's tilted blue sphere, and Neptune's stormy azure face. But those encounters were fleeting, hurried snapshots as the spacecraft sped past, never to return. Since then, Galileo orbited Jupiter, Cassini orbited Saturn, and Juno now probes Jupiter's depths. Yet Uranus and Neptune, the ice giants, have never been revisited. They stand at the edge of our knowledge, shimmering enigmas in the dark. The 2022 Planetary Science Decadal Survey, a document setting exploration priorities for the next 20 years, placed a Uranus orbiter at the top of the list. The logic is compelling. Uranus is a world of extremes, tipped over on its side, its magnetic field oddly offset, its seasons lasting 84 years, its moon still largely unexplored. Voyager 2's flyby in 1986 revealed a strange, pale world with few clouds, but hints of dynamism. A dark spot that later disappeared. Winds racing beneath a bland exterior. Moons like Miranda with fractured terrains and evidence of upheaval. An orbiter would transform Uranus from a distant mystery into a known world, probing its atmosphere, magnetic field, and moons in detail. We would finally learn what drives its bizarre tilt, what lies beneath its atmosphere, and whether its moons conceal oceans of liquid water. Neptune, too, awaits its return. Voyager 2's 1989 flyby astonished scientists. Supersonic winds, the Great Dark Spot, and geysers erupting from its moon, Triton. Triton is likely a captured Kuiper Belt object, with a retrograde orbit and a surface reshaped by cryovolcanism. It may harbor a subsurface ocean, making it one of the most intriguing candidates for life in the outer solar system. A Neptune orbiter with a Triton lander could answer profound questions. What drives Neptune's fierce winds? How does its offset magnetic field operate? Does Triton's ocean exist? And if so, what chemistry stirs within it? Neptune, the Storm King, still keeps its secrets. Secrets that a dedicated mission could unlock. Missions to Uranus and Neptune are not only about these planets, they are gateways to exoplanet science. The most common type of exoplanet discovered so far is the sub-Neptune, or mini-Neptune, planets larger than Earth, but smaller than Neptune. Yet we have no such planet in our system. Uranus and Neptune are our only analogues, and they may be the keys to understanding thousands of alien worlds. By studying their atmospheres, magnetospheres, and interiors, we gain templates for interpreting exoplanet data. Every spectrum from a distant sub-Neptune will be clearer if we first understand our own. Closer in, new missions are preparing to revisit Jupiter and Saturn. Europa Clipper, set to launch in the mid-2020s, will orbit Jupiter and fly past Europa dozens of times, mapping its icy crust, probing for plumes, and searching for signs of a subsurface ocean. Its instruments will measure the thickness of Europa's ice, the chemistry of its surface, and the potential for habitability in its ocean. At the same time, ESA's JU, ICE, JU, PIT, ITYM, ONS, EXPLORER will explore Ganymede, Callisto, and Europa, becoming the first spacecraft to orbit a moon other than Earth. JUICE will investigate Ganymede's magnetic field, its suspected ocean, and its role as a world in its own right. Together, Clipper and JUICE mark the beginning of a new era of outer solar system exploration, focused not only on planets, but on the secondary worlds that orbit them. Saturn, too, has unfinished stories. The Dragonfly mission, scheduled to launch in 2027, will send a rotorcraft to Titan. It will fly through Titan's thick atmosphere, land at multiple sites, and sample the chemistry of dunes, riverbeds, and methane lakes. Dragonfly is more than an explorer. It is a laboratory, designed to search for prebiotic chemistry and perhaps even signs of exotic life. Titan is a natural test for life beyond Earth, a world with a thick atmosphere, complex organic molecules, and a dual potential of methane-based surface chemistry and water-based subsurface oceans. Dragonfly could reveal whether Titan is not just an alternate Earth, but an alternate biology. Meanwhile, dreams of a return to Enceladus stir in scientific circles. Cassini showed us plumes venting from its south pole, carrying water, salts, organics, and hydrogen, all the ingredients for life. Future mission concepts envision orbiters, or even landers, that could fly through the plumes, analyze samples, and search directly for biosignatures. Enceladus is tantalizing because it may be the only place beyond Earth where life could be detected without drilling or digging. The ocean vents its contents into space, waiting for us to catch them. A single detection of amino acids, lipids, or isotopic ratios could change our place in the cosmos overnight. To enable these missions, technology is advancing. Nuclear power systems will be vital for operating in the dark, cold reaches beyond Mars. Advanced propulsion may shorten travel times, perhaps solar electric drives or nuclear thermal engines. Instruments are becoming smaller, smarter, and more autonomous, able to analyze samples and adapt to discoveries in real time. Artificial intelligence will guide spacecraft through complex tasks, maximizing science. Return without constant direction from Earth. In this way, exploration of the giants is not just about science, but about pushing the limits of engineering and imagination. Looking ahead, the next century may belong to the giants. Just as the 20th century saw the first steps on the Moon and the mapping of Mars, the 21st may see orbiters around Uranus and Neptune, landers on Titan and Triton, probes into Enceladus's plumes, and perhaps even sample returns from icy moons. Each mission will deepen our understanding not only of the giants themselves, but of planetary systems everywhere. They will test our definitions of habitability, expand our models of planetary formation, and perhaps answer the greatest question: are we alone? Philosophically, these missions carry weight beyond science. They represent humanity reaching outward, driven by curiosity, daring to send fragile machines across billions of kilometers to touch alien worlds. They remind us that knowledge is not free. It requires time, effort, and generations of commitment. The fact that we prioritize Uranus, Neptune, Europa, Titan, and Enceladus shows what we value. Not just exploration for its own sake, but exploration that may reveal whether life is a universal story or an earthly anomaly. In the end, the giants are not only destinations, they are future frontiers, waiting to be explored, demanding the best of our technology and imagination. Every mission we send is a step into the unknown, a reminder that the solar system is vast, rich, and still mysterious. Voyager gave us glimpses. Galileo and Cassini gave us stories. Juno, Clipper, JUICE, and Dragonfly will give us revelations. And beyond them, Uranus and Neptune wait, their secrets untouched since Voyager's fleeting flybys. The giants are not finished chapters, but open books. And the next century is when we will begin to read them in full. For most of human history, the giant planets were distant lights in the night sky, objects of myth rather than places. Even today, after centuries of telescopic study and decades of spacecraft exploration, they remain impossibly remote. Jupiter is 500 million miles away, Saturn nearly 1 billion. Uranus and Neptune are so far that sunlight takes hours to reach them. Yet as space exploration advances, a new question emerges. Could humans one day live among the giants? Could their moons, with their icy crusts and strange atmospheres, become our outposts in the outer solar system? The idea may seem fantastical, but Titan and Callisto, two of the giants' largest moons, offer surprisingly plausible opportunities. Titan, a world to inhabit. Among all the moons, Titan stands out as humanity's most promising destination. Larger than Mercury, cloaked in a thick nitrogen atmosphere, Titan is unique. Its atmosphere, with a surface pressure 50% greater than Earth's, provides natural shielding from radiation, a vital advantage so far from the Sun's magnetic protection. Unlike airless worlds such as the Moon, Titan's sky would protect settlers from cosmic rays and solar storms. In this sense, Titan is safer than Mars, which has only a thin atmosphere and no magnetic shield. Titan's atmosphere is not breathable, It lacks oxygen and is dominated by nitrogen and methane. But its density makes flight easy. A human, with wings strapped on, could glide through Titan's sky. Drones, aircraft, and balloons would be highly efficient, opening the possibility of aerial exploration and transport. On Titan, the dream of human flight could be realized in a way Earth could never allow. Resources also abound. Titan is rich in hydrocarbons, methane and ethane lakes, dunes of organic particles, tholins raining down from the sky. Its lakes could provide fuel for spacecraft, split into hydrogen and oxygen, or burn directly in engines designed for cryogenic conditions. Water ice is plentiful, available for life support and agriculture. With nuclear power for warmth and chemistry, a Titan colony could be largely self-sustaining. It would not be an easy life, but it would be a possible one. The main challenge is temperature. At minus 180 degrees Celsius, Titan's surface is lethally cold. Structures would need insulation and heating, and machinery would require adaptation. Yet cold is a simpler problem than radiation or lack of resources. With modern technology, humans already build bases in Antarctica and under the oceans. Titan's environment, though alien, is within reach. It is conceivable to imagine domed habitats along methane lake shores, drones buzzing overhead, and humans venturing into the orange haze, pioneers of a world that is both alien and eerily Earth-like. Callisto, a base beyond radiation. If Titan offers resources and atmosphere, Callisto offers safety. This outermost Galilean moon lies far beyond Jupiter's deadly radiation belts. Closer in, Io, Europa, and Ganymede are bathed in intense radiation from Jupiter's magnetosphere, lethal to humans within hours without shielding. Callisto, however, orbits far enough away to be outside this danger. With its ice-rich crust, stable geology, and relative isolation, it is one of the safest places to consider a human base in Jupiter's system. Callisto's ice and rock could supply water and oxygen, while its surface provides abundant raw material for construction. It lacks the geological activity of Europa or Io, meaning fewer hazards and a stable environment for long-term infrastructure. A base on Callisto could serve as a staging ground for deeper exploration of Jupiter's moons, a gateway settlement where humans live and work, while sending robots to probe Europa's ocean or Io's volcanoes. NASA has even studied Callisto as a potential site for a human outpost. Its location offers gravitational stability and resources, while avoiding the extreme dangers of radiation. Solar power is weak this far out, but nuclear reactors could provide reliable energy. In this vision, Callisto would not be a home in the traditional sense, but a hub, a foothold on the frontier, a place where humans begin to extend their reach beyond Mars and the asteroid belt. Human presence among the giants would change everything. It would extend our civilization into the cold outer reaches, transform moons into settlements, and turn exploration into habitation. The challenges are immense. Distance, radiation, cold, isolation. But so are the rewards. Titan and Callisto could serve as refueling stations for deeper journeys, laboratories for studying exotic chemistries, and perhaps even sanctuaries for humanity's survival in the long run. If Earth faces catastrophe, Titan and Callisto could be among the places where human life continues. Living on these moons would also transform our culture. To step outside on Titan and see Saturn's rings towering overhead, or to walk on Callisto and watch Jupiter's vast storms fill the sky, would be to inhabit landscapes of myth made real. Such sights would reshape our imagination, just as the Apollo missions reshaped our vision of Earth. Colonies among the giants would not only be survival strategies, they would be spiritual revolutions, expanding the human sense of place. The idea of living among the giants carries profound symbolism. It would mean that humanity, once confined to a single small planet, had joined the families of the great planets. We would become participants in their stories, not just observers. Titan and Callisto would cease to be distant objects in telescopes. They would be home. The giants, once gods in myth, would become neighbors in reality. To live under their skies would be to accept our place in a cosmos far larger and stranger than Earth alone. Philosophically, these outposts represent the merging of exploration and existence. They would not just be research bases, but new cradles of culture, places where human societies adapt to alien conditions. Life on Titan, with its orange haze and methane lakes, would foster different myths, metaphors, and ways of seeing. Life on Callisto, under Jupiter's looming presence, would cultivate other kinds of imagination. In this way, the giants' moons would not only host humans, they would reshape humanity itself. Titan and Callisto stand as beacons of possibility. They are not easy, but they are achievable. They represent the next logical steps after Mars and the asteroids, the first places beyond the inner solar system, where humans could establish lasting footholds. To live on Titan, or Callisto, would be to cross a threshold, from a species of one world to a species of many. The giants, long seen as distant powers, may yet become our partners in survival. Their moons transformed into stages of our future. The great dark spot exemplified Neptune's mystery. It was not fixed like Jupiter's great red spot, which has endured for centuries. Instead, when the Hubble Space Telescope observed Neptune in the mid-1990s, the great dark spot was gone, dissipated or hidden. New dark spots appeared elsewhere, forming and fading over years. Unlike Jupiter's eternal tempest, Neptune's storms are transient, unstable, chaotic. They are born, live, and die within decades, making the planet a dynamic stage of constant change. The Storm King does not hold one throne, but constantly reshuffles its dominion. The bright methane clouds that often accompany these storms add to the drama. Voyager saw them racing at high altitudes, white against the cobalt sky, casting long shadows. These clouds form when gases rising within storms cool and condense, much like water clouds on Earth. But on Neptune, the temperatures are minus 220 degrees Celsius, and the clouds are made not of water, but of frozen methane. They drift in the supersonic winds, breaking and reforming, sometimes forming bright streaks near the dark spots. For observers on Earth, they are the most visible features, clues to storm systems shifting beneath the haze. What drives Neptune's storms? The leading explanation is internal heat. Unlike Uranus, which radiates almost no excess heat, Neptune emits more than twice the energy it receives from the Sun. This internal heat source may come from slow contraction of the planet since its formation, releasing gravitational energy, or from the decay of radioactive elements in its core. Whatever its source, the heat stirs the atmosphere, powering winds and storms. Neptune is a paradox. Farther from the Sun than Uranus, yet far more active. Its storms are proof that planetary weather is not a simple function of solar distance, but of hidden engines within. Neptune's storms also highlight the role of its tilted and unstable magnetic field. Some researchers suggest that interactions between the field and the solar wind inject energy into the atmosphere, adding to its dynamism. The planet's rapid rotation, once every 16 hours, also contributes, whipping gases into bands and jets. Together, heat, magnetism, and rotation create a perfect recipe for atmospheric violence. For planetary science, Neptune's shifting storms are a lesson in impermanence. Where Jupiter offers a record of continuity, Neptune offers one of change. Its storms are not eternal monuments, but fleeting dramas, born of turbulence and energy flow. To study them is to glimpse the instability that may characterize many exoplanets, especially those far from their stars. Neptune shows us that giants can be restless, their atmospheres never still. Culturally, Neptune's storms have captured the imagination as symbols of mystery and power. Images of the great dark spot and its companion clouds, set against the deep blue planet, have been likened to cosmic paintings, abstract works of art created by physics. The Storm King moniker is apt. Neptune is less a serene planet than a restless monarch, forever raising tempests, forever shifting its face. For poets and dreamers, it has become an emblem of volatility, of hidden fires in cold places, of energy where none should be. The storms also remind us of perspective. Neptune's winds, violent and immense, would be utterly destructive to us, yet from afar they appear as delicate features, wisps of shadow and light. They embody the paradox of planetary weather, immense in scale, yet fleeting in form. Neptune's atmosphere is a place where chaos and beauty are the same, where violence is expressed as elegance. For future missions, Neptune's storms remain a prime target. An orbiter could watch the birth, growth, and death of dark spots, measure wind speeds over time, and probe the depths with infrared and microwave instruments. By monitoring how storms evolve with the seasons, each lasting decades, we could learn how long-term cycles drive planetary weather. Neptune is not just a planet to visit once. It is a world to study continuously, to watch as it changes and surprises us. In the end, Neptune's storms embody the essence of the planet. A king crowned not with rings, but with tempests. Supersonic winds, methane clouds, transient dark spots, all tell of a world that defies expectations. It is the cold giant that burns with hidden energy, the distant planet that refuses to be quiet. Neptune is not a frozen relic, but a living world of storms, a reminder that even at the edge of the solar system, violence and beauty can thrive together. If Neptune's storms reveal its surface drama, its magnetic field exposes a deeper chaos hidden within. Like Uranus, Neptune's magnetism defies the simple, symmetrical models we are used to. Earth's field, though tilted by about 11 degrees, remains aligned with its spin and anchored near its center, giving compasses a predictable north and south. Jupiter's and Saturn's fields are stronger and broader, but still centered and relatively stable. Neptune's, by contrast, is tilted by 47 degrees from its axis of rotation and offset from the planet's core by nearly half its radius. It is a magnetic field gone rogue, crooked, lopsided, and in constant flux. Voyager 2's 1989 flyby provided the only direct measurements of Neptune's field, and what it found stunned scientists. The field was not a neat dipole like Earth's, but a complex multipole, with several competing poles of varying strength. The main magnetic poles were not even close to the geographic poles, and the center of the field was shifted dramatically away from the planet's physical center. As Neptune rotates every 16 hours, this tilted off-center field causes the entire magnetosphere to wobble and tumble like a spinning top about to fall over. In practical terms, the magnetosphere is a storm of its own, a constantly shifting shield wrapped around a storm-driven world. This instability produces an asymmetric magnetotail, the region where the magnetic field is stretched by the solar wind. Instead of trailing neatly behind the planet like Earth's magnetotail, Neptune's twists and spirals like a corkscrew, coiling through space as the planet spins. Charged particles trapped in this tail are flung about in unpredictable ways, creating auroras that flicker irregularly across Neptune's skies. Unlike Earth's or Jupiter's, Neptune's auroras are not locked to the poles, but wander across latitudes, appearing where the skewed field connects with the solar wind. To watch them would be to see curtains of light suddenly blaze at unexpected places, chaotic lanterns in the deep blue dark. Why is Neptune's magnetic field so unusual? The answer likely lies in its interior. Unlike the gas giants, which host deep oceans of metallic hydrogen generating stable dynamos, Neptune and Uranus are ice giants. Their interiors consist of a rocky core surrounded by a thick mantle of ices, water, ammonia, and methane, compressed into exotic ionic forms under high pressure. In these layers, molecules break apart, creating oceans of charged particles capable of conducting electricity. The dynamo that generates Neptune's field may arise not from deep within, but from these shallower ionic oceans. This would produce a magnetic field that is unstable, multipolar, and offset from the center as Voyager observed. If true, Neptune and Uranus may represent an entirely different class of planetary magnetism, one more common in the galaxy. Many exoplanets discovered so far are mini-Neptunes, worlds between Earth and Neptune in size, likely with icy mantles. If their magnetic fields resemble Neptune's, then the chaotic, offset magnetospheres we see here could be the norm, not the exception. In that sense, Neptune is not an outlier but a template, offering us a first glimpse of how magnetism works in the most abundant kind of planet beyond the Sun. The implications for habitability are significant. Magnetic fields shield atmospheres from erosion by stellar winds, preserving conditions where life might arise. A chaotic field like Neptune's may provide uneven protection, allowing radiation to stream through in some regions while blocking it in others. On exoplanets, this could mean climates of patchy radiation, auroras at strange latitudes, and magnetic environments very different from Earth's. Neptune, then, is not only a curiosity, but a laboratory for imagining alien worlds. Neptune's magnetic field also highlights the theme of impermanence. Where Earth's field reverses every few 100,000 years, Neptune seems to wobble continuously. Its offset nature suggests that the dynamo may shift over relatively short timescales, producing a field that is always in flux. If we could observe Neptune over centuries, we might see its magnetic poles drift, merge, or even vanish, replaced by new ones elsewhere. This dynamism makes Neptune not just a storm king of winds, but of magnetism itself. Voyager 2's brief measurements left far more questions than answers. How deep is the dynamo? What role does Neptune's rotation play in its instability? How do its auroras change with seasons? Without an orbiter, we can only speculate. Yet the very strangeness of Neptune's field is reason enough to return. By probing its magnetosphere, we would not only solve Neptune's mysteries, but also expand the science of dynamos, shedding light on worlds across the galaxy. Culturally, Neptune's magnetic chaos has been less celebrated than its storms, but it deepens the planet's mythic character. Named for the god of the sea, Neptune carries within it a field as shifting as waves, as unpredictable as tides. Its magnetosphere coils like a whirlpool, auroras flash like lightning over dark waters, and its offset poles drift like currents beneath the surface. Neptune's field is the ocean of magnetism made real, an unseen sea roiling around the blue planet. Philosophically, Neptune reminds us that not all order is symmetry. Nature often prefers lopsidedness, imbalance, and flux. Earth's neat dipole may be comforting, but Neptune shows us another face of magnetism, dynamic, unstable, and no less real. It challenges us to broaden our definition of what is normal in planetary science. If Neptune's field seems alien, it may be only because we are provincial, mistaking Earth's stability for the cosmic standard. The Storm King laughs at such assumptions, reminding us that in the universe, chaos is its own kind of order. For exploration, Neptune's magnetic field is one of the most compelling reasons to send a mission. Instruments could map it over time, track auroras, measure plasma flows, and test dynamo models. In doing so, they would give us not only Neptune's truth, but a framework for exoplanets. Every detection of a magnetic signal from a distant star system would be read in light of what we learn here. Neptune's field is not only its own enigma, it is a key to the galaxy's planets. In the end, Neptune's magnetism fits its character. It is the planet of storms, of winds faster than sound, of tempests that form and vanish. Its magnetic field is a storm too, a storm of charged particles and shifting poles, tumbling through space in a restless dance. If Jupiter's field is a fortress, and Earth's a shield, Neptune's is a whirlpool, unstable, asymmetric, but enduring. It protects, distorts, and reveals all at once. In Neptune, the Storm King's dominion is not only of clouds, but of invisible forces, as chaotic and beautiful as the winds that rage above. Neptune's storms may dominate its atmosphere, but its moons tell the story of its past. The planet has at least 14 known satellites, ranging from irregular fragments to one of the strangest and most magnificent worlds in the solar system, Triton. Together, these moons whisper of capture, collision, and chaos. They are not a family born with the planet, like Jupiter's Galilean moons, but a collection assembled through violence. A legacy of Neptune's role as a sculptor of the outer solar system. The crown jewel is Triton. Larger than Pluto, Triton is a world of paradoxes. A captured Kuiper belt object orbiting Neptune backwards. A frozen surface that is nevertheless alive with geysers. A body that should be dead, but instead hints at hidden oceans. When Voyager 2 flew by in 1989, it revealed Triton as an icy enigma. A world of pinkish-white plains, nitrogen frost, and dark streaks left by erupting plumes. Triton is unlike any other large moon, and its peculiarities make it a keystone for understanding not only Neptune, but the Kuiper belt beyond. Triton's most astonishing feature is its retrograde orbit. Unlike most moons, which circle their planets in the same direction as the planet spins, Triton moves the other way. This is a sure sign it did not form with Neptune, but was captured. The capture likely occurred when Triton, once a dwarf planet in the Kuiper belt, encountered Neptune billions of years ago. Gravitational interactions, perhaps involving another large body, slowed Triton enough for Neptune to claim it. This event would have been catastrophic for Neptune's original moon system, destabilizing or destroying any large moons that once orbited there. Triton's presence, then, is both a treasure and a tombstone, marking the violent reshaping of Neptune's history. Voyager's close-up images of Triton astonished scientists. Instead of a cratered ancient surface like most outer solar system moons, Triton showed smooth plains, ridges, and strange cantaloupe terrain. A mottled surface, unlike anything else. Its youthfulness suggested recent or ongoing geological activity. Most dramatic of all were the nitrogen geysers, plumes erupting from the surface, reaching heights of 8 kilometers, leaving long, dark streaks across the frost. These geysers, likely powered by seasonal heating of nitrogen ice, revealed a world still alive, even in the frigid darkness 30 astronomical units from the sun. Beneath Triton's crust may lie a subsurface ocean, kept liquid by tidal heating. Although Triton's retrograde orbit is slowly decaying, producing internal stress, it may generate enough warmth to maintain water, mixed with ammonia, beneath the ice. If so, Triton would join Europa, Enceladus, and Titan in the growing family of ocean worlds. potential habitats for life. The idea that a captured Kuiper Belt object, circling a storm-driven planet at the edge of the solar system, could harbor an ocean and perhaps life, is one of the most tantalizing possibilities in planetary science. Triton is also significant for what it tells us about planetary migration. Its capture implies that Neptune did not always sit quietly in its orbit, but interacted dynamically with the Kuiper Belt, scattering and capturing objects. Triton may be the largest surviving relic of this process, a frozen reminder of the early solar system's chaos. Studying Triton is, in a sense, studying the Kuiper Belt up close, without sending a probe to its farthest reaches. Beyond Triton, Neptune's other moons paint a complementary picture. Proteus, the second largest, is an irregular, blocky world about 400 kilometers across. Voyager revealed it as heavily cratered, dark and angular, more a jagged fragment than a sphere. Its most prominent feature, Pharos crater, suggests a violent impact history. Proteus is barely large enough to pull itself into a round shape, making it one of the largest irregularly shaped bodies in the solar system. Its dark surface reflects only about 10% of the sunlight, likely composed of radiation-darkened ice and rock. Nereid, Neptune's third largest moon, is even stranger. It follows one of the most eccentric orbits of any moon, swinging from 1.3 million kilometers to more than 9 million kilometers from Neptune. Such an orbit cannot be primordial. It is the scar of past disruption, likely caused when Triton was captured. Nereid may be a survivor of Neptune's original moon system, thrown into a wild orbit by Triton's arrival. If so, it is a relic of the pre-Triton Neptune, carrying the story of a lost system within its path. Neptune also hosts a family of smaller, irregular moons, distant and captured objects resembling asteroids or Kuiper Belt bodies. Their orbits are tilted and eccentric, suggesting they were snared after Neptune's formation. These moons, like Triton, hint at Neptune's role as a collector, grabbing debris from the outer solar system. They provide evidence of how dynamic and violent the region has been, with bodies constantly scattered, captured, or destroyed. Together, Neptune's moons form a story of disruption and survival. Triton, the usurper, dominates, rewriting Neptune's history. Proteus and Nereid, scarred and displaced, survive as remnants. The irregulars drift in eccentric orbits, reminders of capture. Unlike Jupiter's harmonious Galilean moons, locked in resonance, Neptune's moons are a patchwork family, assembled through catastrophe. For exploration, Triton is the irresistible target. Its geysers and youthful surface demand answers. An orbiter could map its terrain, sample plume material, and search for evidence of an ocean. A lander could study nitrogen geysers up close, watching as frost and ice erupt beneath alien skies. Triton is a world that seems designed to astonish. A captured dwarf planet, active, mysterious, and unique. Philosophically, Neptune's moons remind us that violence shapes beauty. Triton's retrograde orbit, its geysers, its possible ocean, all are the result of capture, chaos, and collision. Proteus's jaggedness, Nereid's wild path, the irregular moon's odd tilts, all are scars of upheaval. Yet from this violence emerges wonder. Neptune's moons show that the universe does not shy from destruction, but in destruction it creates new worlds, new mysteries, new possibilities. Culturally, Triton especially has captured imagination. Its geysers have been invoked in science fiction as alien outposts, its retrograde orbit as a symbol of rebellion, its possible ocean as a cradle of strange life. Triton, more than Neptune itself, embodies the poetry of the outer solar system. A jewel stolen from the Kuiper Belt, set in orbit around the Storm King, waiting for us to return. If Neptune's storms and moons show us its present, its gravitational reach reveals its cosmic legacy. This distant planet is not merely an isolated giant at the edge of the solar system. It is a sculptor, shaping the architecture of the outer worlds and the icy frontier beyond. The Kuiper Belt, a vast reservoir of frozen bodies orbiting beyond Neptune, owes much of its structure to the Storm King's gravity. Without Neptune, the Kuiper Belt would not be what it is today, and perhaps neither would Earth. The Kuiper Belt is a disk of icy bodies extending from about 30 astronomical units, Neptune's orbit, to over 50 astronomical units from the Sun. It contains Pluto, Haumea, Makemake, and countless smaller objects, remnants of the solar system's formation. But this belt is not uniform. It is sculpted into distinct populations, resonant objects, classical belt objects, scattered disk objects, and detached orbits that reach toward the Oort cloud. The key shaper of all these populations is Neptune. Philosophically, the allure of moons reminds us of companionship. Earth is not alone, and neither are the giants. Even Pluto, once demoted, is dignified by Charon, locked in a binary embrace. Moons embody relationship, and in them, we see reflections of ourselves. We too are relational, defined by family, community, gravity of another kind. In moons, we glimpse the cosmic version of intimacy. Not solitary wanderers, but companions bound together. Scientifically, moons challenge us, but poetically, they invite us. To imagine standing on Europa and seeing Jupiter loom above, or walking on Titan's shore and seeing Saturn's rings rise, is to place ourselves in landscapes of sublimity. They are canvases for human imagination, places that do not yet belong to us but already shape our dreams. Just as the moon inspired Galileo, Keats, and Armstrong, these other moons will inspire new generations of poets, scientists, and travelers. They are not just objects of study. They are muses, mirrors, and symbols. In the end, the poetic allure of moons lies in their ability to be both real and dream. They are geological, measurable, physical, but also metaphorical, mythic, and personal. They are places we can map and also places we can dream into. They remind us that science and imagination are not opposites but allies. Moons are proof that wonder survives knowledge, that awe deepens with detail. The more we know of Europa's cracks, Titan's lakes, Enceladus's plumes, the more enchanted we become. Knowledge does not dispel mystery. It makes it richer. And in that richness, moons become more than companions. They become reflections of what we seek in the cosmos: beauty, possibility, and meaning. The moon has always been humanity's first mirror in the night. Before telescopes, before science, before writing itself, the moon was there, waxing and waning, governing tides, marking the passing of months. It was a calendar in the sky, a timekeeper that required no invention. Agriculture, ritual, and myth all bent themselves around its rhythm. For ancient cultures, the moon was more than light. It was order, cycle, and symbol. To lose it would have been to lose meaning. This primal intimacy set the stage for how humans have always seen moons, not only as rocks or bodies, but as companions to consciousness. Across civilizations, the moon became a canvas for story. The Greeks made her Selene, the goddess who drove her silver chariot across the heavens. The Romans gave her Diana, the huntress. In China, the moon housed the jade rabbit, eternally pounding the elixir of life. In Polynesian myth, it was Hina, the mother goddess who fled to the sky. In Norse sagas, Mani was chased by wolves, devoured during eclipses. Each culture painted the moon with its own fears, hopes, and desires. The moon was never neutral. It was always a reflection of the human spirit projected into the night. Philosophers, too, have long meditated on the moon. Aristotle used it as the border between Earth's imperfect realm and the heavens' perfection. Galileo, pointing his telescope, shattered that notion. The moon had mountains, craters, shadows, imperfections like Earth. In that moment, the moon became the bridge between worlds, the proof that Earth and heaven were not separate, but one. Philosophically, this was transformative. It dissolved the old divide between up there and down here, revealing a universe continuous with ourselves. The moon was not only our companion, it was our kin. As telescopes revealed other moons, Galileo's discovery of Jupiter's 4 great satellites in 1610, philosophy stretched again. If Jupiter had moons, Earth was not unique. If Saturn's rings were real, the heavens were stranger than anyone had imagined. These discoveries broke geocentrism, humbling humanity. They showed that Earth was not the center, but part of a larger family. The moons of other planets became symbols of plurality, diversity, and cosmic democracy. They forced philosophy to reckon with the possibility that life, too, might be multiple, scattered across many worlds. In art and literature, moons have served as symbols of longing and reflection. The moon often represents the unattainable, a love, a dream, a desire just out of reach. Shooting for the moon became a metaphor for ambition, lunacy for madness, the moon for romance and melancholy. Poets from Libai to Shelley to Neruda wrote under its gaze. Painters placed it in canvases as both light and symbol. Musicians wove it into songs. The moon was more than scenery. It was muse. And as science revealed Europa, Titan, and Enceladus, these new moons began to play similar roles, inspiring novels, films, and visions of alien landscapes. They are the next canvases, waiting for human imagination to inscribe them with meaning. Culturally, moons also embody the paradox of familiarity and otherness. Our moon is close, bright, knowable, yet still mysterious in its influence on mood, tide, and time. Distant moons are alien, shrouded in ice or haze, yet oddly familiar in their rivers, oceans, and storms. Titan feels like an Earth refracted through amber glass, Europa like a frozen sea with secrets beneath, Enceladus like a cosmic fountain. They show us both the familiar and the alien at once. In them, cultures can see metaphors for ourselves. We too are familiar yet strange, stable yet changing, ordinary yet extraordinary. Philosophically, moons remind us of relationship and humility. A moon is defined by orbit, by being bound to another. It is not solitary but relational. In this, moons reflect humanity. We too are defined by relationships, not by isolation. The Earth itself, in turn, is a kind of moon, orbiting the sun, companion to a star. To see moons this way is to see kinship. None of us are alone, all of us are bound. Even at the cosmic scale, companionship defines existence. Moons also challenge our sense of importance. Earth once seemed central. The discovery of other moons made it peripheral. Our moon once seemed singular. Now it is one among hundreds. The giant's moons show us that planet and moon are categories of convenience, not destiny. Ganymede is larger than Mercury. Titan has a thicker atmosphere than Mars. Triton is as dynamic as Pluto. To call them moons is less a statement of essence than of context. Philosophically, this destabilizes our hierarchies. It reminds us that greatness is not defined by labels, that worlds do not need to orbit stars to matter. Finally, moons symbolize hope. They are destinations for imagination and exploration. Apollo made our moon a place we have touched. Future missions may make Europa, Titan, or Enceladus places we have sampled, perhaps even walked. Each moon, represents not only a physical frontier, but a spiritual one, a new stage of meaning, a new layer of story. They remind us that the cosmos is not empty, but rich, not silent, but resonant. They are the echo chambers of our own imagination, reflecting back to us our desire for beauty, truth, and belonging. In the end, the cultural and philosophical impact of moons is profound because they are mirrors. They reflect back what we project: gods, myths, science, poetry, ambition. They shape our calendars, our language, our metaphors. They humble us by reminding us that Earth is not unique. They inspire us by showing us landscapes both familiar and strange. They connect us by embodying relationship and companionship. And as we continue to explore them, they will continue to mirror not only the cosmos, but ourselves, our questions, our hopes, and our need for meaning among the stars. If the 20th century belonged to planets, the age of Apollo on the Moon, Mariner at Mars, and Voyager's Grand Tour, then the 21st century may well belong to moons. They are no longer secondary curiosities. They are the frontiers of habitability, laboratories of exotic chemistry and potential havens for life. The coming century will be defined by missions to Europa, Titan, Enceladus, Ganymede, Triton, and beyond. In them lies not just the promise of science, but of philosophy, culture, and imagination. They are the next mirrors we will hold up to the cosmos and to ourselves. Within a decade, the Europa Clipper will fly past Europa dozens of times, mapping its ice shell, probing for plumes, and testing for subsurface oceans. If the mission detects signs of saltwater breaking through the crust, or organic compounds in the plumes, Europa will leap from possibility to priority, a candidate not only for habitability, but for life. Meanwhile, ESA's JUICE mission will focus on Ganymede, orbiting it for years, studying its magnetic field, its geology, and its hidden ocean. Together, these missions will transform Jupiter's moons from distant enigmas into places of detailed knowledge. At Saturn, Dragonfly will carry the next leap. Unlike rovers crawling on rocky ground, Dragonfly is a rotorcraft, a flying laboratory. On Titan, with its thick atmosphere and low gravity, flight is easy. Dragonfly will leap from dune to dune, lakebed to lakebed, sampling chemistry, measuring weather, searching for complex molecules. It may reveal whether Titan's methane cycle has fostered exotic life, or whether its hidden ocean harbors water-based organisms. Either way, it will force us to expand our imagination of biology. Dragonfly's wings may carry us closer to answering the ancient question: are we alone? Beyond these, concepts for missions to Enceladus remain high on the wish list. Cassini showed us plumes venting from its south pole, plumes carrying salts, organics, and hydrogen. A future orbiter or lander could fly through these geysers, collecting samples for direct analysis. Enceladus is uniquely generous. It shares its ocean with space, inviting us to taste its chemistry. If any mission could detect life outright, amino acids, lipids, or even microbial fragments, it might be one to Enceladus. In a sense, Enceladus is offering us an answer. We only need to accept it. Uranus and Neptune, too, wait for their turn. Their moons, Miranda, Ariel, Titania, Oberon, Triton, are blank pages in our atlases. A Uranus orbiter and probe, prioritized by NASA's Decadal survey, could arrive in the 2040s, beginning the long exploration of ice giants and their moons. A Neptune orbiter with a Triton lander would be even more transformative. Triton, retrograde and active, could be an ocean world, a captured Kuiper Belt object with secrets about the outer solar system. These missions would not only explore moons, but also illuminate the most common type of exoplanet, the sub-Neptune. To study Uranus and Neptune is to study thousands of alien worlds at once. Looking further, the possibilities grow more audacious. Engineers imagine cryobots melting through Europa's ice, releasing submersibles into its hidden ocean. Others dream of sample return missions, bringing back grains of Enceladus's plumes or Titan's tholins to Earth's laboratories. Human missions, though more distant, are not inconceivable. Callisto has been considered as a base, safe from Jupiter's radiation, stable and resource-rich. Titan, with its thick atmosphere and plentiful methane, could support colonies. Its skies alive with flying drones and human explorers gliding on artificial wings. To live among the moons would be to rewrite humanity's story, from children of Earth to citizens of the solar system. The next century will also test scientific paradigms. If Europa or Enceladus reveals biosignatures, we will know that life is not unique to Earth. If Titan shows exotic methane-based life, we will know that life is flexible, able to arise in conditions utterly unlike ours. If Triton or Ganymede hosts hidden oceans, we will know that the galaxy may be filled with such worlds. Moons will determine whether life is rare or common, narrow or diverse. They will answer questions that philosophy has carried for millennia, questions that shape our sense of meaning. Even if we find no life, the discovery will be profound. A sterile Europa would tell us something crucial. Oceans alone are not enough. A lifeless Enceladus would show that chemistry must cross thresholds more difficult than expected. A barren Titan would remind us that atmosphere and complexity do not guarantee vitality. Negative results would not end the story, they would sharpen it. In science, silence is also information. Absence is also answer. Moons will speak, whether through life or through silence, and we will listen. Culturally, the exploration of moons will ripple outward. Just as Apollo transformed Earth's self-image with the sight of the blue marble, missions to Europa, Titan, and Enceladus will transform imagination. We may see posters of Titan's lakes on classroom walls, novels about Europa's explorers, films about life under Enceladus's ice. Moons will enter not only textbooks but myths. They will become part of the human imagination, woven into our art, literature, and philosophy. They will remind us that wonder is not exhausted by knowledge, that awe survives even when mapped. Philosophically, moons will force us to expand our definitions of home and life. We will have to accept that life may not need warmth, may not need sunlight, may not need Earth-like conditions. We will have to accept that humanity's place is not unique, but part of a broader canvas. This will not diminish us, it will enlarge us. To know that the cosmos is fertile is to know that we belong to something greater, that life is not an exception, but a pattern. The next century of discovery will be the age of moons. Europa Clipper, JUICE, Dragonfly, cryobots, sample returns, Uranus and Neptune orbiters. These missions will transform our understanding of habitability. Human exploration may follow, turning Titan and Callisto into outposts, places where we live under alien skies. The cultural impact will be profound, the philosophical impact deeper still. We will know whether we are alone, or whether the giants' children host life of their own. In the end, moons are not side notes. They are central characters in the cosmic drama. They embody intimacy, relationship, possibility. They are mirrors of imagination, reflecting back our own hopes, fears, and longings. And as we step into the next century, they will reflect something more. Our courage to explore, our willingness to wonder, our readiness to embrace a universe richer and stranger than we ever dreamed.